100 kilometers above the Earth's surface lies an invisible frontier, the edge of space. This is the Kármán line, the boundary between our planet's atmosphere and what lies beyond. What does it take to cross that line? To date, some 450 cosmonauts, astronauts, taikonauts, the names all mean the same, have crossed that unseen line. Cold War test pilots to begin with, then geologists, engineers and scientists of one kind or another. Mission specialists now come in all sizes and nationalities. Even politicians and cashed-up tourists have gate-crashed the space party. But how do you earn an astronaut's wings? As Chris Hadfield, the first Canadian to walk in space, has said, an astronaut's life is one of preparation and simulation, and training and support on the ground, and anticipation and visualization. And very, very seldom, almost never, is an astronaut's life about flying in space. In one sense, the key to becoming an astronaut is simple: brute force. But selection for space is an exhaustive process. Astronaut candidates must be fit, physically and mentally, to endure the rigors of training. High intelligence is essential, while bravery is a useful character trait. The current crew of astronauts have trained for work on the International Space Station, while others are working towards missions yet to come. They have one thing in common: they all consider themselves lucky.
I never planned to become an astronaut. I mean, I knew that it's a very small likelihood, and so as a scientist, I knew the statistics, meaning like, okay, if I try to become an astronaut, it probably won't work out. So for me, applying with ESA to become an astronaut was not as much a thing of me believing that I would become an astronaut, but more trying to give my dream a chance that I had, that I knew I was always looking forward or trying to see, do I have a chance to actually go there?
It also helps if you know how to use one of these.
I find my background as a pilot very helpful, just in the way that I've previously been taught how to follow procedures, for example, as a pilot, communication methods, working together in a team in an international environment. All of those sort of skills are very useful in this job.
Of course, I had expectations before I started. But the job as an astronaut is so unique. I think it's difficult to have a realistic sense of what to expect. So certainly some things have been what I expected. I mean, the excitement, the uniqueness, the wonder of human spaceflight is exactly what I thought it'd be. Other things, of course, have been different simply because it's such a unique world to train for a mission.
Astronaut candidates should expect a 2-year period of training and evaluation. Learning to live and work in extreme environments comes right at the start. Movie buffs will recall Key Largo in Florida as an isolated place for Humphrey Bogart. Now it houses NASA's NEMO facility Aquarius, training astronauts for both the ISS and future asteroid missions. Other unwelcoming environments used for isolation and team building include the Sagruta Caves in Sardinia, Italy.
The ESA Caves mission that I was a part of a few years ago, where I spent a week living underneath the ground in a gigantic cave system. The 2 NASA NEMO missions that I've been able to participate in. I mean, all these things are fantastic opportunities in and of themselves. And just having those opportunities without going to space would be fantastic. But so to have them and then to go to space as well is just really it's what makes this job so unique and so fantastic.
Of course, spaceflight training is not easy. I think that's clear. I mean, for 3.5 years, you have to travel almost every 3 weeks. You fly over the Atlantic. You're in different training locations. You spend about 5% of your time at home. And if so, maybe then just a weekend here or there. So it's a challenge.
Training takes us all around the world into every center. I've already done 2 or 3 orbits around the world, but just in a plane going from NASA to Russia to Japan and back to Europe. So it's already, the training as an astronaut in itself is already rewarding. I mean, it's already the dream job. And even better, it gets you to a flight in the end. So there's no time to be bored. There's no time to think too much about what you're doing. Every day you're busy. Every day is a good day. And that's going to continue until the flight.
Use the ladder. Okay. Careful, and I'll just follow you. And we'll sit down there.
Space training in Europe begins at the European Astronaut Center in Cologne, Germany, where trainees learn the essentials of maintenance and repair of onboard systems.
You would be asked to actually either remove or clean or just inspect the filter. We would need to close the ladder.
They also continue their basic EVA training in another unfriendly environment, underwater.
In general, the training at the different locations varies quite a bit. First, there's the technical side, which means like we're training in Japan on the systems that Japan supplied to the space station. In Russia, we're training on the Russian segment of the International Space Station. In the US, we train for the US side. And at ESA, we train for Columbus and ATV, which are the modules that ESA supplied to the space station.
Next, the candidates move on to NASA's larger Johnson Space Flight Center in Houston, Texas, for extensive EVA training.
Training at the JSC is always very busy because we do many different things and it's a huge facility, so we're moving all the time from one building to the other. Like here we are in the building 9, where we have a replica of all the American modules of the space station. So in this building we train for the space station. Some of it is daily operations, some of it is actually off-nominal operations like emergencies, like in these mock-ups in this building. Just yesterday I did a 5-hour emergency simulation with my crewmates, with our full crew complement of 6 people of Expedition 42. And that of course is not something that you would call daily operations. That's something that we really don't want to happen, but we train it a lot because emergencies would put us as crew in danger.
Here we go.
HCN 1.2.
The great thing about being trained on emergencies is that it gives you a state of mind. Having the knowledge, having the training can help you in any situation, in any condition, just like it happened to me during my EVA. It was an unexpected emergency that we had not been trained for, but because you have received training that it's all encompassing, it gives you the state of mind where you look forward to the solution rather than focusing on the problem.
EVAs, extravehicular activities, sound routine enough. But spacewalks, as we know them, are among the most dangerous duties an astronaut must carry out. Preparation and safety-conscious planning are critical.
Behind me, you see a lot of equipment which is related to the airlock operations in case of a spacewalk, so we train this here as well. But there's also another completely different facility, which is the Neutral Buoyancy Lab. That's a huge pool, and in there we train for spacewalks underwater.
Neutral buoyancy training tanks are in place at ESA's Cologne facility and at Star City in Moscow. But JSC has the biggest.
EVA training is fantastic. It's physically difficult. It's one of the most challenging parts of the training, but it's also one of the most realistic. When you're in the pool for 6 hours, you get tired, but at some point you really think you're on the ISS. You look around you, and there's a structure everywhere. Sometimes you even get disoriented because that's what happens in space. It's like a 3D labyrinth of technology. It's a maze of technology.
There is so much going on here because we not only train space station, but robotics, spacewalks. So it's a very complex training system, and it's very exciting to be part of it.
I think one of the hardest parts of the astronaut's job is to retain all this different information over the 2.5-year period from being assigned to actually launching. Yeah, there's an awful lot of information on the Soyuz, on the space station itself, robotic training, EVA training, the list goes on. So to try and retain all that, the way that they do that is just by having refresher training really along our path to launch.
JAXA, Japan's space agency, trains astronauts in the operation of the country's ISS contribution, the Kibo experiment module, with its space exposure platform.
I guess it has a very Japanese flavor to it. I mean, the content and the way the content is presenting and delivered is pretty much standardized. But of course, you know, the instructors are Japanese. They have that very polite, very kind Japanese way about them.
In Saint-Hubert, Quebec, the Canadian Space Agency's Mobile Servicing System Operations Complex schools astronauts in using robotic arms on station.
Here's a station at scale, and here's the robotic arm, also at scale. It moves, and we can plan our maneuvers. As you can see, the main challenge is to not hit anything while you're moving this arm, because all you got, really, when you're working, you come here. There's this workstation. You got a couple of camera views to work from. You got your hand controllers to move the arm, and you get the, some computer displays and a bunch of switches here on the left. That's all you got. So you really got to think ahead how you're going to maneuver this arm without crashing into anything, because of course that would be a very bad day on orbit.
Star City near Moscow in Russia was the birthplace of manned spaceflight. It remains a key training center where all ISS-assigned trainee astronauts go through the program.
When you first start in Star City, you immediately feel like you're part of something bigger than just your own personal history, because your personal story, because you see people who've been here since the beginning. There's even supposedly Yuri Gagarin, his wife, is still living here, even though she's very old, she's still living in the vicinity. So you just cross people in the corridor, and they've known all those guys, and I was just a kid, and those guys were already in human spaceflight. So you try to learn as much as you can, you try to do your best for the technical side of the job, and try to interact as much as possible with the people, because they're so experienced that they have a lot to give you.
Expecting the unexpected is a basic training principle, like landing off course after the mission or touching down in the Siberian tundra. As NASA has no manned flight hardware of its own at present, the agency purchases seats on Russia's Soyuz spacecraft. All astronauts must be trained on the Soyuz systems, which poses a problem of its own. Everything is, of course, in Russian.
All the documentation's in Russian in the Soyuz spacecraft, and of course all the conversations in Russian as well, which is the reason for us having all of the Russian lessons during our training flow.
Not only must you know the Russian language, when in Russian spacecraft, you must also wear Russian spacesuits.
When the Sokol space suit actually pressurizes, things do become much more difficult to work because you're kind of fixed in your seat in a very rigid location, and it's hard to bend your arms and bend your fingers in fact. So even just sort of reading the board documentation can be quite difficult. But hopefully you won't be pressurized when you do a normal descent. Hopefully the spacecraft will come down without any problems and your spacesuit will be much softer, which makes it easier to move.
Here in Star City, I'm using most of my time in the Soyuz simulator together with my commander. Suddenly it's starting to feel a lot more real, you know, when you're sitting in the Soyuz and you're really going through the whole launch and landing sequence. You can feel that you're getting close to the date, and it's very, very exciting.
It's a very well-oiled machine, this flow to launch, and I'm confident that, you know, by the time every astronaut flies, you're really ready to go. You're prepared in every way.
As things stand, an astronaut bound for a 6-month mission to the ISS needs up to 5 years training, a requirement which will, in all likelihood, be intensified for future missions to deep space. The ISS will probably be used as a long-duration astronaut training facility for missions to Mars and beyond.
We are also all people that are selected to be able to get along with each other. That's kind of like the way you select astronauts nowadays for long-duration space flights. You really want to have people that are balanced, that are easy to get along with other people.
So much of our work up there is determined by the visiting vehicle traffic, and that's a very dynamic phase because we're not quite sure exactly which vehicles are going to arrive when.
I got 18 centimeters.
And these vehicles bring up a lot of science, they bring up a lot of hardware that determines when the EVAs are done, and also they of course determine the robotics activity that goes on to capture the vehicles. So when you're not quite sure what the visiting vehicle schedule is like, you're not quite sure exactly what science and when it's going to be done on board the space station.
One 6 months increment for the whole crew is around 300 experiments, out of which there's 55, 60 for ESA. So there's a wide array of domains like medicine, technology, material science, fluid science, everything you can think of. We're trying to make the most of the conditions in space and the microgravity to get results that wouldn't be possible to achieve on Earth.
So one of the things I've learned is you just have to be extremely flexible, and we get trained on how to do tasks that may be planned 6 months ahead of our mission and maybe planned 6 months after our mission, so that should there be some flex and those activities fall within our increment, then we're trained and we're ready to do those as well.
There's some leftover smell.
Whoa. Not good.
Not good.
Looking out of the window is really one of the most fantastic experiences that you can have from the International Space Station. Our Earth is so beautiful, and yet when you look outside you see that the atmosphere that surrounds our Earth is so thin. It's merely like an eggshell around an egg. It's so fragile, and the vulnerability, the fragility of our planet is very, very visible from on Earth. You see this blue ball and then above nothing, just black, absolutely nothing in this immense universe. And I would hope that more people would be able to fly to space, more maybe of our politicians, decision makers would be able to fly to space and really see the vulnerability of our planet, so that we can finally start doing something about climate change.
Been used. So
we're just so prepared. All the emergencies, all the possible failures, we train them over and over and over again. So we're supposed to be able to handle any situation. We sat in the simulator hundreds of hours. We know the systems inside out. So there's nothing really that we fear, I think, on the technical side.
Even with all that training, astronauts are well aware of the dangers of space flight. Riding a rocket full of explosive fuel, living in an enclosed environment with a thin sheet of aluminium between you and hard vacuum, solar and cosmic radiation, bullet-like micrometeorites and space debris. Then there is the threat of onboard fire or mechanical failure, and to cap it all off, the fiery return to Earth. There is, however, one problem that returning astronauts cannot avoid, and that's gravity.
When you get back home, of course, I will always remember this was the same for my first flight or for my second flight. The moment they open up the hatch and you feel this fresh, cold air coming into your capsule. This is really something. And you're out there, of course, in the steppe. You have this real soil kind of smell that you have. It's really feeling fantastic. And then they get you out of the capsule. And the first thing, of course, that you want to do is to contact your family, your friends, saying, I'm all right, everything is great. We will see each other tonight. And then you just want to rest and to sleep because you're so tired, of course, from this long day of coming back. And also the gravity is really then having an impact on your body. You can't, it's difficult to stand up. It's everything that you have to lift. It's hard, it's difficult. And this takes a couple of days. But after a couple of days, of course, you recover well. We have a very good recovery program here at our European Astronaut Center. Our people are really very focused on getting the astronaut back up to the level as he was before the flight as soon as possible. And then, of course, it's again, after a while, business as usual.
I'm reaching the end of my career and I'm being able to do a last flight and really, again, put at work for myself, but also for everybody else, all the knowledge and know-how that I've acquired during this year. It's a very great opportunity, and I'm really happy that I've been assigned for this.
There is another way of crossing that unseen line on the edge of space, by paying your own way as the ultimate tourist. A number of wealthy individuals have already done so. Soon enough, it will become cheaper and accessible to the ordinary mortal, provided he or she can pass the medical.
You know, when our test pilots and wonderful team that run Virgin Galactic say that we're ready to go, then I'll be ready to climb in and be the first passenger as such, to go to space and to become an astronaut, and from there, hopefully, thousands of people will follow me.
Launching payloads into space is no straightforward matter. Historically, rocket launches have been used as the proverbial swords into plowshares. Missiles designed to carry atomic warheads now send satellites and probes into the solar system. Ironically, it's one of the few exploits mankind undertakes that doesn't occur in nature. rocket science is all it's cracked up to be. Bringing together the mathematical, engineering and mechanical skills required to design, build, test and successfully launch a rocket into space is a mammoth technical undertaking. So many countries and corporations have the capacity for launches nowadays that they appear commonplace.
0.
Only the keenest science geeks seem to watch them these days, unless, of course, something goes wrong, and then everyone is hooked. Space launchers fall within several categories, based on their payload or cargo weight and where it needs to get to. The unsung heroes are the commercial satellite delivery systems, providing light and medium lift capability to low Earth, polar or geosynchronous orbit. Many countries such as Argentina, Iran, North Korea and Ukraine boast their own homegrown systems. Even New Zealand, in a joint venture with the US, is developing a budget CubeSat launcher called Electron. The Soviet Union, first to harness its ballistic missiles, has several workhorses like the Proton rocket family, the Rokot, Zenit, Dnipro and sea-launched Volna systems. Ukraine in its current form inherited some of these rocket systems after the Soviet breakup. Like the Proton, these systems use highly toxic fuels. They will be phased out by 2030 and replaced by the Angara rocket system, which is both environmentally friendly and modular in construction to save launch costs. The Angara rockets are designed to put payloads ranging from 3,800 to 24,500 kilograms into low Earth orbit. The Russian Soyuz rocket, designed in the 1950s, has proved to be the most reliable rocket system ever flown. Upgraded to version 2, it will continue to operate alongside Angara. The Russians are also looking to develop a replacement for their aging Soyuz TMA spacecraft, with several designs already on the drawing board. Japan has its Epsilon satellite launcher, which can lift 1.2 tons into orbit. Their H2 continues to evolve, the B variant delivering cargo missions to the ISS.
Ignition. And liftoff. Liftoff of the HTV on a journey to the International Space Station.
補給機コウノトリ4号機を搭載した H2B ロケット4号機は平成25年8月4日午前4時48分46秒に種子島宇宙センターから打ち上げられました。
India's ISRO space organization has developed a range of vehicles for delivering satellites, either to polar orbit with the PSLV or geosynchronous with the GSLV Mark II. India has big plans for space development, one of which is to build a man-rated capsule. The Chinese Long March series of rockets has made steady progress and powers China's manned space program. Even they are becoming environmentally conscious as well. The Long March 5 heavy thrust cluster rocket, with a loading capacity up to 25 tons, is by far the largest carrier rocket China has.
Compared with previous rockets, the biggest difference is the non-toxic propellant in hydrogen-oxygen engines and LOX kerosene engines that will not pollute the environment. And we applied serialisation, unitisation and modularisation to design and manufacture.
Another major player in launch capability is the European Space Agency ESA, with its facility at Kourou in French Guiana. The Vega launcher, developed by ESA and the Italian Space Agency, continues to operate for light payloads. The real European success story, however, is the Ariane 5 heavy lifter, the workhorse for ESA and the CNES. But it too will shortly be replaced by Ariane 6. Currently under development, it will use components in common with the new Vega C rocket.
Ariane 6 will reduce the cost of a launch service by 50% compared to today. So you have to realize that in just 4 years, we are reducing the cost of a launch service in Europe with 50%. And that is, of course, a major step. And if you think about Ariane 6 in a double launch configuration, we are able to offer a price which is really, really attractive, also in comparison with the competition. So the situation that we will have with Ariane 6 and Vega C will be exactly the same in terms of what we can launch as we have today with Vega, Ariane 5 and Soyuz. We can launch every satellite with these two launches in the future. It is very clear that the international competition is getting more and more intensive. This is very clear, especially from the American side. We can see that there is a systematic, let me say, aggressive approach of the market to gain market share by American suppliers of launch services.
When NASA, intent on pursuing the Orion and SLS deep space system, relegated low Earth orbit to the private sector, the commercial floodgates were opened. The United Launch Alliance took over the existing NASA hardware and services and now operates the venerable Atlas V, along with the Delta II and heavy lift Delta IV systems. It's now developing the Vulcan rocket for future expansion.
Main engine ignition, 2, 1, and liftoff. Liftoff of the United Launch Alliance Delta IV Heavy rocket carrying the NROL-37 mission.
The Vulcan Centaur vehicle will be a high-performance, lower-cost, best value vehicle. We're going to maintain our mission success history that we've had with Atlas and Delta. So we've got two main engine suppliers, Blue Origin with the BE-4, which is a natural gas-powered engine, and we've got the AR-1 from Aerojet Rocketdyne, that is the RP-1 configuration. Both of those teams are making good progress. We've been through CDR with the Blue Origin engine. We've been through EDR. They're both on a plan to get to engine testing this year, and they're both on a path to support our late 2019 launch date.
With that mission now opened up to commercial ventures, many companies are rushing to build better, safer, and most importantly, cheaper rockets. Two private service suppliers for NASA are Orbital ATK and SpaceX. These are the first two contracted by NASA for current ISS resupply payloads and planned manned transfer missions. Orbital uses Minotaur rockets, which are in reality the MX Peacekeeper ICBM, which was never fully deployed as a result of disarmament treaties. Orbital has modified these rockets to carry scientific payloads. Their heavy payload launcher is the Antares 230 and 232, which can lift 8,000 kilograms into low Earth orbit, including the Cygnus spacecraft. With the Falcon 9, Elon Musk's SpaceX company is working on the principle of recycling or reusing launch systems to make launches cost-effective. They can now return the main launch stage back to Earth and land it safely, to be refurbished and ready to launch again. Working on their heavy lift Falcon, which will be able to lift 54,000 kilos into orbit, or 13,600 kilograms towards Mars, and then return to the launch site for reuse. Even the Falcon Heavy, however, will be dwarfed by the upcoming NASA Space Launch System. It will tower over everything previously seen, with the capacity to put 130,700 kilograms into orbit or send 52 metric tons into deep space. Its first task will be to fly the Orion crew capsule and a probe to the Galilean moon Europa. Sending humans into orbit is another matter altogether. Here, launchers have to be incredibly reliable and able to lift very heavy payloads safely. In other words, they have to be man-rated. The only two man-rated capsules at present are the Chinese Shenzhou and the Russian Soyuz TMA. Unsurprisingly, they look very alike. The Russians, however, are looking to the future and a crowded commercial market. Their Soyuz has successfully flown over 120 missions, but a new, cheaper capsule called Federation is underway. It will carry up to 6 cosmonauts and will be competing against NASA's Commercial Crew Development Program, which has Boeing and SpaceX delivering cargo and soon astronauts to low Earth orbit. Aerospace giant Boeing's space capsule, the CST-100 Starliner, is to ferry astronauts to and from the International Space Station.
Starliners go.
When you're sitting in the capsule on top of a rocket and the final moments of the countdown are happening, it's exciting. It's like being on the top of that roller coaster when you're a little bit scared, but you're really pumped because this is what you've been working for all your life, taking that next step into exploration.
Over 1 kilometer. Truck deploy. Drugs look good.
California-based SpaceX is developing its Dragon capsule to carry crew to low Earth orbit and beyond. The crewed version of Dragon would carry up to 7 astronauts to the orbiting lab. Blue Origin is a strong competitor to both contractors, but its sights are on the tourist suborbit segment. They too have designed their rocket to return to launch for reuse, and their capsule, the Blue Shepard, can hold 6 paying customers.
Shepard has cleared the tower.
There you have it. There it is, 70,000 pounds of thrust pushing that crew capsule.
The B-3 engine remains on. The booster continues to space.
The drogues are out on the crew capsule. There go the mains. And touchdown of the new Shepard crew capsule. From what we can tell, that was a nominal in-flight test of our escape system. And again, all astronauts on board would have had a pretty exhilarating ride. But
there you go. The booster speed. That tail fire has got set it short. Beautiful.
Wow. There it is.
Touchdown.
What an extraordinary test and a tremendous final flight for both craft.
Their main rival will probably be Virgin Galactic or Vulcan Aerospace with their air-launched systems. Sierra Nevada's Dream Chaser is a small space plane designed to carry 7. The spacecraft is based on a NASA concept vehicle from the 1980s called the HL-20. Having failed to secure a NASA contract, Sierra Nevada has teamed up with Vulcan and European interests to further develop a version of the Dream Chaser. Advances in aeronautical engine design have led to the Sabre.
We're actually at Reaction Engines test site at B9. What is very significant about this is that we are in the process of testing a very, very important development in aerospace propulsion, which is a pre-cooler, a device for cooling the air entering a high-speed engine so that the engine can continue to operate pretty much as normal. This means that we're going to be able to fly at speeds of Mach 5 pretty easily in the future.
It is in effect a rocket engine burning hydrogen and oxygen. That in itself is not unusual, but whilst in the atmosphere the oxygen is taken from the air, cooled to liquid temperatures and fed directly into the combustion chamber, once outside the atmosphere, the engine resorts to the liquid oxygen carried on board, like a conventional rocket engine. Skylon will be powered by 2 Sabre engines and operate like a conventional aircraft capable of flying directly into orbit, transporting 15 tons of cargo into space and returning for a runway landing.
We're looking at a revolution in transportation equivalent to the jet engine, and access to space, access to anywhere in the world within 4 hours is on the cards. Once you've got access to space on that basis, that's the stepping stone to anywhere in the universe, and a very exciting future for the human race.
Although government contracts are lucrative for these private companies, many firmly believe tourism is the way to fund future space development. For those cashed-up civilian tourists, Space Adventures team has designed a circumlunar mission using a unique combination of existing and flight-tested Russian technology. The combination of the Soyuz spacecraft and the lunar module will provide ample living space for your approximately 6-day journey and the fuel required for you to leave low Earth orbit. Perhaps the most ambitious is Elon Musk's SpaceX interplanetary transport system, helping make humanity a multi-planet species. The initial design objective of the vehicle is to launch a variety of missions to Mars and other destinations in the beyond Earth orbit portion of the solar system. The large payload capacity of the launch vehicle, with the ability to place 300 tons into low Earth orbit, places it into the super heavy lift class. The ITS launch vehicle's first stage is designed to be reusable, following a return to the launch site and vertical landing after each launch. What's new on this vehicle is full reusability of even the second stage and the spacecraft as well. Cheap, safe space travel for all is just around the corner. The International Space Station is without question the jewel in the crown of low Earth orbit. Observation post, research lab and classroom all in one. But many other assets orbiting Earth are even more important to our everyday lives, delivering communications, weather observation, global positioning and resource management, and the list is growing every year. Chances are you are watching this program via satellite in one way or another, either transmitted directly or indirectly to your television, iPad, laptop or phone. In other words, you're using technology once considered science fiction. Pushing the envelope, technology must keep up with demand. More data, more reliability and real-time connection. Space test and hardware and technology are on the cutting edge of science, often introducing new methods of gathering scientific information. Demonstrator missions are regularly sent up, flying new engineering solutions to prove the hardware in situ, even without a specific goal in mind.
Technology goes through a whole development cycle, which we call the seamless chain of innovation. We start from the idea and we work along to develop it through our work in the labs, through the work of industry, and especially of small and medium industries, which are the vectors of innovation. But at the end, you need to prove that it works in the real space. And in order to do that, we use these missions that can take the risk of flying unproven technology and demonstrate to the larger missions that they work.
Research laboratories focusing on the next generation of space hardware are dotted around the globe. The UK's Space Gateway Harwell campus, the ESA RAL Advanced Manufacturing Laboratory, supports cutting-edge research and development.
The purpose of the laboratory is basically to assess and pre-screen candidate materials and processes for future space missions. So this will guide ESA, as well as the space community, in focusing their technology investments in the right area.
The lab has extensive on-site testing facilities, such as the ISIS neutron source, the Diamond Light Source synchrotron, and the UK's Central Laser Facility. This year will bring the first launch of a satellite using the small GEO platform, Hispasat 36W1. Small GEO, a telecommunications platform accommodating a wide range of payloads and missions, has been developed in Germany in a public-private partnership between ESA, OHB and the operator Hispasat.
It indeed, because Hispasat and ESA were able to join forces, that we were able to develop a satellite with such a level of innovation. On the one hand, a new platform with a new satellite prime contractor, on the other hand, a payload embarking also a high level of innovation. And altogether, this satellite has been developed, is going to be flown, and we provide very innovative services. So end-to-end, the level of innovation is very high, and indeed, separately, neither Hispasat nor ESA would have been able to undertake such a complex development. With the small GEO, what we have tried to achieve was really to develop a new product in the low end of the telecommunication market. And at the same time, this new product would allow a new prime contractor to become a prominent player of the satellite telecommunication market. That's the OHB, which is the prime contractor of this satellite.
This is a class of satellites that only have electric propulsion on board, which is a high-efficient system that allows achieving important mass savings. So we are able to put in space a satellite with a similar capacity of a full chemical one, but with much lower mass, which means less launcher cost, compatibility with more launch vehicles. And again, this translates in advantages for the operators who have at their disposal more efficient technical solutions for their mission. But it's very flexible, so it can also be used for other geostationary applications.
Another scheduled event in the telecom area is the launch of EDRS-C, expected by the end of the year. EDRS-C is also based on the small GEO platform and will be the first dedicated satellite for EDRS, the European Data Relay Service. It will be the second element of the Laser Relay Space Data Highway. Low Earth satellites encumbered with line-of-sight communications can beam their data upward to geosynchronous satellites via laser, which can then transmit the signal to ground stations at any time.
The small GEO program is just the first step for OHB. OHB has already sold a number of other telecommunication satellites, and indeed this is the start of a product line that will evolve over time, like any other product lines of the other prime contractors operating in the satellite telecom market.
Another area of research has been in cost and time effectiveness in developing satellites. This has led to the CubeSat, several of which have flown in space. Measuring just 10 by 10 by 10 centimeters, these small cubes or nanosatellites have become extremely popular, opening up new possibilities for a wide range of groups previously unable to access space.
We are a small group of students with 2 professors and 2 coordinators, and we had 52 students who did the master's thesis on this project.
It's a great project for the students because it's the occasion to apply practical stuff and not only the theoretical stuff they have learned at school.
Our satellite is the telecommunication satellite. We use the D-Star protocol for the radio amateurs to communicate around the world.
This is really a special moment when we can see that finally the people is installed on the platform that will carry it to space on board the Soyuz launcher.
So it's a great feeling to be here in Kourou, in French Guiana, with the satellite almost in space and normally ready to roll.
Using off-the-shelf technology, CubeSats have been launched from the ISS and piggybacked onto other satellite launches. They will soon be deployed to Mars, asteroids, and further afield. GPS is used every day by people on the ground thanks to global positioning satellites from the United States. But GPS is not the only system in orbit. Russia has its GLONASS constellation, China has its own Beidou system, and Europe is building the Galileo network.
The initial services is a stage in the program whereby there is sufficient infrastructure is made available in space, satellites around the globe who circle around, plus infrastructure on the ground which control the satellites, provide the navigation signals. Enough of that infrastructure is ready so that the system can be used. The use is still not fully 100%, hence the word initial services.
These constellations are not exclusive. Galileo will also use the GPS system for even more accuracy, and the US is tying in with the Russian GLONASS for extraterrestrial services. In other words, they will enable spacecraft to utilize the positioning system in almost any orbit around the Earth.
Some of the signals are available only during a certain percentage of the day. The satellites move around and not all of the day you have sufficient satellites inside. But there is enough to start. And this is a very important moment in the program, an excessively important moment, because this actually shows to the world that the system is really going well. The performance we actually can provide, we know, is excellent. And of course we will continue building out the full constellation, but the users can actually now start using the satellite system.
The European Galileo navigation system is nearing completion. More satellites will be launched this year, adding to a constellation which will eventually number 22.
Under initial services, there will be 3 services provided. One is the so-called open service. This is for the mass market. This is where people will use their smartphones, their navigation devices in cars, which will have Galileo enabled chips inside, which will receive both Galileo and GPS in combination, and it is the combination of the 2 systems which will be used to determine the position of the user. For ESA and the European Commission, when we started with satellite navigation, it was of course not quite clear how really important satellite navigation was going to be. And we had studies, we had our insights in it, and we knew that it would be important. But now we really see how important it is, particularly looking in the future, where we're going to need to have a sufficiently developed satellite navigation infrastructure to support autonomous driving and all sorts of other applications.
NASA has already developed specialized GPS receivers for space application. The Navigator receiver from NASA's Goddard Space Flight Center first flew in 2009 and proved to be very successful. A number of future missions in HEO, GEO and MEO plan to work with this receiver using its high-sensitivity signal acquisition and tracking capabilities. NASA's JPL has also developed the Blackjack flight GPS. Now being flown aboard an Argentine satellite, the system looks at how the GPS radio signal is distorted or delayed along its path. A typical GPS signal can plot a position to within around 22 yards. Blackjack can pinpoint its host satellite continuously to an accuracy of about 1 inch. 18 receivers are on orbit, while another system under development called the Triple GNSS or Tri-G will be able to track GPS and GNSS signals, including the Russian GNSS and European Galileo navigation constellations. All of our spacefaring nations continue their Earth observation work in collaboration with a number of organizations. The refinement of orbital positioning and unhindered high-speed communications mean more new technologies craft are being added to the armada of observation satellites. They include Europe's Copernicus program with no fewer than 3 Sentinel satellite launches. In March, Sentinel-2B will be launched carrying a wide-swathe, high-definition multispectral imager. With Sentinel-2A already on orbit, both Sentinel-2 satellites will monitor land cover, vegetation and water pollution.
Now that we get Sentinel-2B to fly together with Sentinel-2A, there's a couple of improvements that we get so far. We have a revisit of 10 days. With Sentinel-2B, we will have a revisit of 5 days. That means we see every spot on Earth every 5 days. That will help, of course, also to avoid the clouds or to have the chances higher to have no clouds in the various regions of the world. Both together, Sentinel-2A and 2B will also improve the performance of the services that are using the data.
Sentinel-2B is contributing to a constellation of Sentinel satellites, which really provides data over decades in different domains and with different instruments on board. So therefore, we're building up a fully operational system, which is enough incentive for industry to invest and to rely on this information in the future.
Sentinel-2A is already supporting a lot of applications. They're ranging from, for example, agricultural applications where we can do yield forecast to forest monitoring where we, for example, see deforestation. And besides that, there's plenty of other applications like inland water where we can look at the quality of the water. We can support river monitoring, but also coastal areas where we look at the changes in the coastal regions. On top of that, we recently changed also to acquire the Antarctic region, so we're also now looking at ice and glaciers.
Later in the year, 2 more Sentinels, Sentinel-5P and Sentinel-3B, will follow. The Sentinel-5 precursor mission is a satellite dedicated to monitoring our atmosphere at a high temporal and spectral resolution. It also offers increased cloud-free observation.
A second satellite, which is a replica of the first one, is of course shorter to develop and to test. The main effort when you develop a new system is put on the first spacecraft, where you discover basically all the early problems in equipment production, software validation, integration and test. All the specifications, plans, test procedures are ready whenever you start building your second spacecraft. And this is, of course, a large benefit. The second spacecraft, let's say, was realized in 1.5 year time. The cost as well, of course, of a recurring spacecraft is much cheaper than a proto-flight spacecraft. You could say basically it's 50% of the price of the first one.
Sentinel-3B is a multi-instrument mission to measure sea surface topography, sea and land surface temperature, and ocean and land color.
We are addressing a number of issues that relate to the development of new science, but also operational missions. For example, Earth Explorer missions, the scientific missions, but also we are preparing the next generation of Sentinel missions for Copernicus. In the next 5 to 10 years in Earth observation, we will face a number of challenges, some of them coming from outside. Big data, constellations, commercial companies entering our domain. And I think there we really have to see, as ESA, as European Space Agency, a public institution, how we can best react to these external challenges and position ourselves with our programs to really address these challenges from our perspective.
Demonstrating new laser technology, ESA is launching the ADM Aeolus satellite. ADM stands for Atmospheric Dynamics Mission. It will provide global observation of wind profiles. With this mission, ESA hopes to further our knowledge of the Earth's atmosphere and weather systems. Space is a hazardous place. A key part of maintaining reliable satellite services is keeping a weather eye out. The Earth is constantly being bombarded by damaging solar storms and charged particles ejected from the Sun. These could knock out satellites and even communication systems and power grids on the ground. Geomagnetic storms, solar X-ray and proton flux, coronal mass ejections and sunspots all are monitored continuously. The Earth is also surrounded by a cloud of debris from 60 years of human space activities, space junk which could also damage satellites. Near-Earth objects also threaten the Earth and could collide with our planet. All these threats are monitored under ESA's Space Situational Awareness Program, which the Operations Directorate hopes to see continuing to evolve.
We want to protect our assets in orbit and on Earth against impacts from space, may it be from space weather or risks from near-Earth objects. And we also want to protect our spacecraft in orbit from risk, for example, coming from space debris.
The Interagency Space Debris Coordination Committee, or IADC, is a forum of 14 nations brought together to exchange information and to research various aspects of this problem. Numerous working groups are studying methods of protection and threat mitigation. No matter what hardware is orbiting Earth, it can only make scientific observations. Only our human perception of the beauty that lies below can help us fully appreciate the planet we call home. Our seafaring nature has translated well to the space age, sailing out into the unknown in search of riches of one kind or another. While Europe and Asia continue their interest in the resource-rich moon, the United States and NASA have set their sights on nothing less than manned missions to Mars. Can they manage to go shore to shore on the most dangerous of unknown seas, deep space? With low Earth orbit harnessed, it's time to look further afield. To build a spacecraft and rocket system to reach Mars is a mammoth undertaking, but if successful, it will return the United States to the top of the space achievement ladder. The first requirement? A space capsule able to carry 6 astronauts for a long period of time and return them safely to Earth. Orion is its name, and it has flown once already in a shakedown. The next flight will be an unmanned test mission past the moon, followed by a third manned mission. The components for the vehicle are developed around the country, tested and checked, then passed on for assembly. The minutest bolt and circuit is designed, tested, redesigned and tested again. Slowly the systems come together with the aid of some breakthrough technology, particularly in manufacturing methods, new materials and processes. The first thing to notice is that NASA have gone back to the classic conic shape like Apollo, the safest design yet devised. Avionics, control systems, computer software, and a glass cockpit, all state-of-the-art.
And the concept was to go with a glass cockpit, and what that means is that the instruments are all images on a computer screen. They are all on the glass. So rather than flipping a physical switch, the crew brings up a computer screen and flips a virtual switch, a little icon of a switch or icon of a valve. And with the exception of 7 panels right around the computer screens, which have about 60 switches, that is all of the cockpit of Orion happens on the glass. One big benefit is a weight savings because you don't have to have a physical switch. And having a physical switch, not only is there the weight of the switch, but you also have the weight of the wire to the switch. And you have to have the weight of circuitry that takes that wire and feeds it into the vehicle computers.
Because of Orion's size, its all-important heat shield is the largest one ever made, and new processes were required to manufacture it.
The Orion heat shield has got to be able to withstand landing loads on the order of 300 to 400,000 pounds. Because we're returning potentially from the moon or beyond, and the flight duration from the time in which you commit to a return to the time you actually land, the weather conditions on Earth can be substantially different or difficult to predict. And so the Orion spacecraft has to be able to land in the ocean in a wide range of sea conditions, wave height, wave slope angle, and horizontal winds. That is what's driven us to a skin stringer architecture that utilizes a thick laminate composite skin bolted to a titanium substructure.
We bond on an ablator called the AVCoat. The ablator is the thermal protection part of the heat shield. The very outside of the ablator actually gets hot enough that it decomposes, and that's the ablation part of it as opposed to an insulator like a shuttle tile.
Then come the ancillary structures and equipment that will ride with the capsule. The escape tower, designed and tested, will pull the capsule away from the main rocket in the case of an emergency. Adapter separation from the rocket's upper stage. Parachute deployment. The connecting adapter to the EMS. The EMS is the service module attached to the Orion in flight, supplying oxygen, water, power and heating. Built by ESA, it is based on their very successful ATV program, which delivered supplies to the ISS. It will also provide the main engine thrust for deep space maneuvering.
We have, in particular, very tight schedule in front of us. So everybody's working under a high pressure to meet the dates, and this requires a very close collaboration.
I see a very motivated team, and so far as an agency we are quite happy with the performance of the European industry.
The US Navy is tasked with retrieving the capsule from the ocean. At first they train in the pool, then calm waters, then the Pacific, and finally the real thing. This is the RS-25, the Ferrari of liquid rocket engines and the main engine from the Space Shuttle program. Economically repurposed for the Space Launch System, 4 of these engines will power the main stage of the rocket. The main solid rocket boosters of the shuttle program also have a renewed life in the SLS. With another 2 segments added, the boosters will thrust for over 2 minutes.
This project has been a real fun effort in trying to take a heritage booster that had many, many years of reliability and great performance and evolve it into something bigger and better.
When we first undertook this design and qualification for the new booster, part of the mission was to make the booster more affordable and more modern, and of course it had to be completely redesigned for a new mission. It's a larger booster, and the mission profile is sufficiently different to where pretty much everything on the inside of the booster is different. There's well over 1,000 individual processes. Working with our customer, we were able to identify several hundred areas of improvement.
We've got totally new avionics on this vehicle versus what we had on shuttle. It's state-of-the-art.
Bigger and more powerful than any previous launch system, the SLS has been under development for some time. Designing it is one thing, building it another. In new or refurbished factories and assembly shops, the body of the largest rocket ever to fly is being constructed one piece at a time. The massive hydrogen tank takes shape. The smaller oxygen tank soon follows. The interim stage for the manned flight is another hydrogen-oxygen motor supplied by cryotanks fabricated with new technologies.
So to design and manufacture this tank, we use new materials. We process the tank by automated fiber placement. The benefit of that is we can lay down the material quickly, which provides us a low-cost operation and a very lightweight tank.
We've worked on this program for 29 months, and when we started, we'd never built a tank of this size by the methods that we did. We did automated fiber placement and fluted core, just developing the robotic fiber placement equipment and way to make the skirt in one piece was a large challenge.
Each exacting piece is fabricated, test articles are run through the mill, vibration tests, vacuum tests, acoustic tests, stress tests. Nothing is left to chance. New technology and new materials for a new generation of space exploration.
So this test, there were several things that we looked at. This was the first time we used those thermal knives to start the deployment sequence, and that allowed cut some tethers that then allowed the solar array to deploy. We wanted to test the locking mechanisms to ensure that it locked properly in space, because anything that could possibly go wrong, we wanted to see test down here so that we can ensure a successful flight.
It's all about technology. If you don't
develop technologies for the future, you won't go where you want to go. So composites will decrease the weight of the tanks. It'll increase the payload performance of the launch vehicle. It'll give us, it basically enables things that we don't have today.
Soon the mighty rocket will lift human beings up further than ever before. The flight to Mars will be a long one, too long for a crew to sit in a capsule. Habitat and supplies will also be lifted to orbit and assembled. Several companies have been selected by NASA to carry out studies for a suitable system to do the job. A bit of competition is always good for invention. Bigelow Aerospace, with its Expandable Activity Module, or BEAM, currently being tested on the ISS, will develop and test a prototype of X-Base, a 330 cubic meter expandable habitat. Boeing of Houston is developing a modular habitat system that leverages more than 15 years' experience in designing, developing, assembling on orbit, and safely operating the International Space Station. Lockheed Martin will refurbish a multi-purpose logistics module into a full-scale habitat prototype that will include integrated avionics and ECLSS. Orbital ATK will mature the mission architecture and design of their initial cislunar habitat concept based on the Cygnus spacecraft that now supplies the ISS. Sierra Nevada Corporation's space systems will study and refine a flexible architecture and concept of operations for a deep space habitat that draws on the lessons of 3 to 4 commercial launches to construct a modular, long-duration habitat. NanoRacks, in conjunction with its partners, Space Systems Laurel and the United Launch Alliance, referred to collectively as the Ixion team, will conduct a comprehensive feasibility study regarding the conversion of an existing launch vehicle's upper stage, or propellant segment, into a pressurized habitable volume in space.
So if you're designing spacecraft to be in the Mars orbit, then the studies we're doing on Space Station can be applied and help us design more durable spacecraft for that Martian atmosphere. MISSE stands for the Materials International Space Station Experiment. We do study the durability of polymers in terms of their mechanical properties with radiation exposure. And we hear a lot about the radiation exposure impact on humans for flights to, say, Mars. But polymers and other materials that are used on spacecraft can also do great from radiation, and that's one of the things I study. The MISSE 8 experiments do take a little bit of time because we do very careful dehydration measurements of the samples after they've been in space. What we found is that the Teflon erosion rate is highly dependent on the amount of sunlight and possibly the heating too. You need to know which of these environments it's going to be exposed to because it'll erode at a different rate depending on the environment.
Assembling spacecraft in orbit and fueling them for the long journey to Mars sounds simple enough. On-orbit refueling is anything but simple. NASA have been developing a system for unmanned refueling for quite some time and have a test article on board the ISS.
We can take a pick-and-place robot, put the tool wherever we need it to be, and all it needs to do is drive that tool because the smarts are in the tool. So that's what we learned from working on Hubble, is you put a smart tool with the astronauts and accomplish, both things. You've got smart tools and astronauts working together. Now we're putting smart tools with robots and trying to accomplish the same type of things we did on Hubble.
Aimed at developing capabilities for servicing, even refueling spacecraft on orbit, RRM is like doing precise surgery at a distance, doctor and patient separated by the void and vacuum of space. It's tough, but the payoff is huge.
Robotics can do things that humans can't do in terms of precision, in terms of control, holding a particular spot for 6 hours while engineers on the ground debate what to do. We can't ask a human to do that.
The robot is a very stiff, rigid interface. It's not forgiving like an astronaut's hand. So we have to take that into account. When you push on something really hard with the robot, you build up really large contact forces. When the astronaut pushes on something, his wrist might give, he's got his own internal sort of software compliance running. But in order to accommodate the robot so we don't break anything, we have to build features into the tool, features into the software, just getting the robot to go where you want it to go. And, they don't position precisely, so you have to do things like build lead-in into the tool. An astronaut can probably just get it right on there because he's right there. So we do have to do things to make them, very specific to robotic operation.
That task successful? Next stop, Mars. The first manned mission to Mars will probably only orbit the planet, checking out all the gear and processes, even launching communication satellites, and finalizing landing sites in preparation for the next mission, which will then make the descent to the surface. And that has a whole new set of problems to overcome. Unlike the Moon, Mars has stronger gravity, about 0.6 of Earth's, but it does have an atmosphere where parachutes can be used, although the atmosphere is very thin and not very deep.
Well, it's a funny thing about Mars, but if you take the average of the planet, the average height of everything in the planet, it turns out that most of the north is 2 kilometers below that, and most of the south is 2 kilometers above that. And it's just, we always land in the north because there's a lot more atmosphere. If we land in the south, it's like 4 kilometers less of air to come to a stop. In fact, at the altitude of the mountains in the south, the Mars Science Laboratory was still supersonic as it was descending into the crater that it was reaching in the north.
Assuming the need to pre-position habitats, supplies, and equipment on the surface prior to a human landing, NASA and its partners are looking at several solutions. One is the HIAD, or Hypersonic Inflatable Aerodynamic Decelerator. This is basically a very large inflatable heat shield, much larger in area than the payload, able to slow the craft considerably faster than a standard spacecraft heat shield. Plans are to test the system on a payload from the ISS, utilizing a Cygnus resupply spacecraft. Once lower in the atmosphere, parachutes will further slow the payload to an altitude low enough for rocket engines to take over. Morpheus and the Zombie flight systems have matured over the last few years and are capable of delivering cargo to a planet's surface autonomously, avoiding rough terrain or other obstacles without human intervention. adding yet another building block to our human effort to explore the solar system. As the latest successes and failures come and go, Mars continues to give up her secrets. Invisible clouds are revealed with ultraviolet light, and the search for the source of methane continues with ExoMars. As we prepare to land humans on the red planet, getting there is one thing. Staying long-term is another. Can we really conquer this planet? The joint European and Russian ExoMars made a successful launch with great applause and journeyed uneventfully to Mars.
Our instrument is devoted to the measurement of trace gases by measuring the solar radiation passing through the atmosphere of the red planet.
Some scientists are trying to determine the local origins of methane gas. Is it a sign of life?
We're interested in looking at where the trace gases may be coming from. So, for example, if methane is there in abundance and you see it locally coming from a particular place, you'd like to know whether it's got a volcanic origin, whether it might be old gases that have been trapped in ice that's then released due to sublimation processes, things like that. It doesn't have to be biology. And it's important to recognize here that I'm a little bit of a skeptic. You know, I don't go for this life business. I try to keep the other guys honest.
ExoMars made a perfect orbit insertion around Mars and commenced flexing its considerable technological muscle. Returning high-resolution images and stereoscopic observations, enabling highly detailed three-dimensional maps to be created. However, the mission didn't go entirely to plan. The lander half of the probe, the Schiaparelli lander, made an ideal separation from the orbiter and commenced a textbook descent. The heat shield functioned as expected, all systems go. The drogue chute, then the main, were deployed correctly. Then the curse of Mars struck. 1 second's worth of erroneous data was passed on to the onboard guidance and navigation control system. When this odd data was merged into the computer's algorithm, it generated a false altitude reading, placing the lander below ground level. This triggered the premature release of the parachute and back shell. Braking thrusters fired and the lander's on-ground systems began operating, thinking it had landed. Unfortunately, it was still 3.7 kilometers in the air, and the universal laws of gravity took over, the lander smashing helplessly into the ground. Satellites overhead soon located the parachute and back shell, and then the lander itself, looking like a squashed bug on a windscreen. The lander was, however, a technology demonstrator, and the problems that arose could be quickly remedied. So ESA is still fully confident of the technology and will proceed with the next lander containing the ExoMars 2020 rover. With the latest analytical technology, the rover will drill down as far as 2 meters into the Martian soil, looking for those elusive microbes. This is the Interact Centaur rover from ESA. It can be remotely controlled from orbit by ESA astronauts. NASA has its own version. They're one of the tools for future investigations on Mars. The proof of concept in Earth orbit will make it a reliable tool on Mars. Astronauts can maneuver the robot to a test table, then perform very fine operations with a number of tools and devices. It could even help assemble hardware and habitats on the Martian surface while astronauts orbit overhead. NASA's Curiosity rover continues its epic journey across Gale Crater, covering over 14 kilometers in its 3 years of operation. It will soon be replaced by its smarter big brother, Mars 2020 rover. Built on the same configuration, the 2020 rover looks strikingly similar to Curiosity, with some improvements. A landing hazard redirect feature to avoid any rocky landings, new wheels and treads for better climbing, audio microphones to hear what's going on, and a rock core sampling drill. One of the main goals of the Mars 2020 mission will be to determine the potential habitability of the planet for human visitors. Scientific instruments on board include an advanced stereoscopic imager, environmental sensors for temperature, wind speed and direction, pressure, humidity and dust particle size and shape. Pixel is an X-ray fluorescence spectrometer for chemical analysis of Martian soil. RIMFAX, a ground-penetrating radar to study subsurface geology, and Sherlock, an ultraviolet laser spectrometer for the study of fine-scale mineralogy and organic compounds. The final instrument package is MOXIE, a technology demonstrator designed to generate oxygen from the carbon dioxide in the Martian atmosphere, a critical piece of kit if humans are going to survive on Mars. It will generate oxygen for fuel and breathing. Mars's atmosphere is predominantly carbon dioxide, plus trace amounts of argon, nitrogen, oxygen and carbon monoxide. Its mean pressure is 600 Pascal. That's about 0.6% of Earth's air pressure at sea level. So another vital piece of equipment is the spacesuit.
In the future, I'm looking forward to spacesuits that are much more of a tool for the astronaut, that is more integrated with the human, and is less of an encumbrance and more of a help.
Several spacesuit designs are underway. There are many specific requirements. The flexibility to walk and move on a low-gravity planet, for example, and the ability to bend down and pick things up. They must also be able to illuminate the way forward. Ease of access for donning the suit is important, as are clearly a pressure garment and thermal insulator for the low pressure and temperatures on Mars. The latest prototypes, like the Z2 and the PXS, are going through extensive development for surface use. The Z2 meets the walking and flexibility requirements. PXS is a more traditional style of suit, but also quite flexible.
My main responsibilities on this spacesuit is the suit control assembly, and that's the box that sits right here on the front of the suit. And it allows the crew member to control their life support components, such as their cooling and their pressure, and it also controls a lot of the electronics, such as the radio and the volume, and they can see some of the data that's coming back and forth from the suit computer to that display. So one of the great things about this job is that after designing the box, I'm able to get into the suit, since it's one of the smaller sizes, and we can actually see what the limitations are, with my own hands and eyes, and not just hear that secondhand from another test subject that would be looking at the same data. And then to take that back and then to go build the next prototype and incorporate the changes that need to be made so that it works better the next time.
Another critical element for surviving on the Martian surface is power. The sunlight reaching Mars is just a little more than half of what we receive on Earth. In addition, there are regular dust storms, and solar power may not be sufficient of itself. It will have a role to play, but other sources of electric power may be required. NASA has been developing fission power plants for such requirements, working on 2 systems. The less powerful technology demonstrator unit for spacecraft and surface operations requires watts of power numbered in the tens or 100s. Kilopower addresses the need for surface power from 1 to 10 kilowatts for human habitats and scientific exploration in the harsh environments of Mars and beyond. The journey to Mars is a long one, not in kilometers as such, but where the scientific, technical, and engineering hurdles that need to be overcome are concerned.
What are the things they need to know to be able to safely land, live, and return from Mars? The scientific knowledge, the technologies that we need that can make human exploration of Mars happen are within our grasp. In our lifetime, we actually can see humans land and work on Mars. A major step in this direction of planning has been the definition of what we call human exploration zones. This is a region we will land, we will live, we will use resources in many different ways, and we want to go to a variety of scientifically exciting locations. Do it in ways that humans, and only humans, can do.
One drawback: humans are fragile. To function correctly, they have a specific set of requirements: atmospheric pressure, air to breathe, water and food for nourishment, rest and sleep, and protection from radiation. Mars offers very few, but it does have an abundance of radiation. Mars habitats have been the subject of years of engineering and technical research. NASA has even thrown open the doors to students and architects to help design and develop suitable accommodation. There are minimum requirements around the number of occupants and length of stay. With limits on payload weight and mass, using local resources like sand, rock and ice to develop habitats has been strongly recommended. The 3D print competition threw up some very good ideas and designs, some of which NASA is developing further. The three finalists were Team Lava Hive, Team Gamma, and Team Space Exploration Architecture and Clouds Architecture Office of New York. Their ice house included all the components required to assemble the habitat in situ on Mars. The vehicle lands at the designated site and deploys several robots and water storage assets. The robots set about building a secure base, utilizing local sand sintered together with lasers. An inflatable plastic membrane is then deployed along with internal airlocks. The robots source local water, which is used to 3D print the inner lining of the membrane. Water is an excellent shield for radiation, and being translucent, it allows sunlight in. Hanging gardens and windows add a touch of home. NASA Langley has developed the ice dome concept from this prize-winning concept. Creating a colony on another planet really is a mammoth task. Leaving aside the training, technology and traveling, not to mention the money, building a functional, self-sustaining village will need people from all walks of life. Apart from the scientists, geologists and prospectors there to do the primary job, people will not cope with living in prefabricated temporary shelters. A town will have to be built from local resources. Engineers, builders, fabricators, electricians, plumbers and mechanics will all be in great demand. So will IT and communications experts, doctors, nurses, pilots, farmers, botanists, and the list goes on. On the other hand, not everyone gets the chance to colonize an entirely new planet, so that is one draw card. If Mars 1 is any example, it seems there will be plenty of volunteers for this dangerous work. One question hasn't been asked yet, and it's of fundamental importance. Can humans live long-term in space or on another planet with reduced gravity, less sunlight, and lower atmospheric protection? One proposal before NASA at the moment is the multi-generational independent colony for extraterrestrial habitation, autonomy and behavior, which contracts nicely to MICEHAB, and it's exactly what that name suggests. MICEHAB is a spacecraft and autonomous support system to study the long-term generational health of mice in Martian gravity. The vehicle would be placed in a stable orbit close enough to the Moon to be within easy reach by manned missions. The MICEHAB would be deployed and spun up to Mars-like gravity. It would then support the growth of a large mouse colony for a year or longer, studying reproduction and maturation of lab mice through multiple generations, which is to say, much faster than human subjects. The vehicle would house multiple levels of mouse enclosures designed to be serviced and cleaned by an onboard robot. The system would take care of feeding, watering and cleaning the mice, including their medical care. Breeding would be selectively controlled over generations in the low gravity. The mice would also be studied for any physical, behavioral or metabolic changes. The project would also collect data on deep space radiation and the hazards posed to humans. The robotic systems would also provide an in-situ demonstration of autonomous activities like maintenance for long-duration deep space missions. From time to time, astronauts would dock with the habitat to collect data and specimens. MICEHAB will allow humans to prepare to live independently from Earth in space and on the surface of Mars, and help answer that critical question we started with. Could humans survive long-term in low-gravity environments? Astronauts and cosmonauts, we've seen them train and study for years to enable these select people to work and live aboard the International Space Station. We have seen countless hours of their activities live on television and in the media. With this wealth of experience and insight behind them, what do they think when they return to Earth? Without exception, these spacefarers simply cannot wait to get back into space. Astronaut Paolo Nespoli is on his third space mission.
It's what I call becoming an extraterrestrial person. You know, it's losing your earthling things, and now you are really an extraterrestrial person because you don't think anymore about gravity, you don't think anymore about up or down, you think about what you need to do and position yourself so you can do it in the best way. You need to get used to working, to live first in space, being able to be very confident in the environment where you are. You need to be able to learn to translate extremely efficiently without banging into things. You need to be able to carry stuff. You need to be able to learn how to move around and do things, and how to sleep efficiently, how to work efficiently. And this takes like a month and a half. So after that time, you are fully ready to work, and that's why 6 months, because you have the capability then of performing at 100% of your capabilities, and then, you know, after 6 months, I think people are ready to go back to Earth and, you know, taste again the food, smell the air, see their friends, their family. For me, it was an exhilarating experience. I mean, I found this thing of trying new things. I find it really good. I felt I was like a little kid trying to do something, you know, try to get crazy and get inventive. And sometimes I thought, I should try something like that. And I said, that's not possible. It's never going to work. And then you try it, and you see that it opens up all sorts of other things that you never thought about it. And that it's a very good feeling. I mean, this feeling of discovery. The astronaut in space is one of the resources of the space station, and the control center want them to use as much as possible, so they have to make sure that they can work. In fact, we do work from 7:30 in the morning until 8:30 in the evening. That's the working day, and Houston and the other control center make sure that it's filled with activities. About 50% of that time is used for maintaining the station. We need to fix things, we need to move equipment, we need to change experiment, we need to load and unload spacecraft, we need to prepare for spacewalks. This is an important part. And then another 30 to 40% is actually scientific work. I am an engineer, an aerospace engineer, but I will do experiments that have to do with genetics, with medicine, with life science, with metallurgy. And we have a complex set of experiments spanning 360 degrees. Which is a sealed environment. I'm going to open up. It's a little bit going to school, yes. It's a little bit like the adrenaline that pumps in when you are in an exam, and you want to, from one side, you want to show off. You want to show all the things that you know. In the other side, you need to be careful, because some of these things can be very tricky, and it's easy to misunderstand something or getting too much involved in one thing and forget about the other one.
There are currently 16 active members of the ESA astronaut corps. Paolo is among the oldest. At 60, this is his third flight into space.
I feel really honored to be able to fly in space again. It's a very nice experience for me. I'm looking forward to use all of this investment that the agency have made in the past year to qualify me, all the personal investment that I made in get qualified and stay qualified, and use it again, go to space and be useful. I mean, I'm 60, but I'm going there, and I'm expected to perform as anybody else and carry out my task, and I'm looking forward to do what is needed and possibly a little bit more.
Other ESA astronauts who have experienced their first missions in space are already in training for their next. Alexander Gerst has spent 165 days in orbit with 6 hours of EVA experience. Even though he is well aware of the amount of work and effort that lies ahead, he's keen to get back into space.
It's a fantastic feeling to be back in training, of course. You can see the training facilities right behind me, and you can see why it's so interesting. I mean, this is like a full-on mock-up of the space station, so this is really the closest you can get on this planet to how the space station feels and looks like. And I've, of course, missed it a little bit after my last mission. I returned in 2014. That's 3 years ago. So it feels great to be back in that working mode.
He'll certainly be continuing some of the research he started in orbit back in 2014. On top of this, he'll be fulfilling a new role, that of ISS commander, a job which requires a high level of responsibility for the station and its crew.
Of course, a new part to my training is that on my next mission I have the added responsibility of being the ISS commander, and to me that's a great honor. So I'm very humbled by the trust that people have in me to actually command this fantastic space station. But of course, it comes with a big responsibility also already in training. So it means I'm right now not only responsible for my own training. Like in my last mission, I had to make sure that I'm trained and I can do everything that people need from me in orbit. Now I have a crew to take care of.
Another key element of the returned astronaut's life is to impart their considerable experience in order to help train the next rookie astronauts. Matthias Maurer, ESA's newest astronaut, has been training with astronauts Tim Peake and Luca Parmitano, both of whom boast extensive EVA experience.
It's actually a lot of fun because I can relate what I'm doing on the ground to what I did in orbit, and it gives me perspective to how it's going to be while I train. And as a matter of fact, our feedback to the instructors is very well received because we can improve the training that we receive just by getting our experience into the equation.
It's great to be back in Houston training again. I'll be in the neutral buoyancy laboratory very shortly with Matthias Maurer, the German astronaut, so my ESA colleague. Really looking forward to that as well, trying to sort of impart some of my knowledge from my spacewalk and share my experience with Matthias. Here in Building 9, of course, it's great to be back, reminiscing about my time on the space station, but also learning about the new developments that are constantly changing on board the space station.
Don't tether to this D-ring on the bottom, that's only for the battery. The other thing too is that you can shove this all the way in here and then this foot.
I have so many fantastic images and wonderful memories of my 6-month mission to space. If I was to have to choose one highlight, I would probably say the spacewalk was the highlight. Just going out of the hatch and seeing space, seeing Earth, and looking back at the space station from inside a spacesuit, that really was another order of magnitude over and above just the experience of going into space.
You put your toolbox down here, and your toolbox will stay because the water will keep it and the gravity will keep it. In space, you put your toolbox down, you look back, and it's gone, and it's up there, and it's all over the place. So, and all the tools inside your toolbox will all be floating around a lot more. So, the microgravity is really difficult in space.
I was at the NBL earlier this week, and just seeing the suit-up operations and seeing the suited guys going down for their spacewalk training, it really brings into perspective what the realities of a spacewalk are versus the NBL. And you know, there aren't that many. The NBL really is a fantastic place to train for a spacewalk. It's the best place that we can train on Earth.
Crew book side? Yes, and actually this is a good opportunity whenever you're heading out the airlock.
All European astronauts get training on how to operate in a spacesuit, in the American spacesuit. And so we need to learn how the spacesuit works, how it functions, and also how difficult it is to work inside such a suit. It's very limiting, and like a work that takes us 5 minutes here on the ground, in space it takes me half an hour. And afterwards my entire body aches, and it's hard work outside on the station.
And try to do hand over hand. And Matthias, you don't have to ingress the APFR. We could have drivers.
I pause for a second to figure out which... I hope that I get the chance to do a spacewalk, because all my colleagues told me spacewalk, it's like the best experience of your space flight. Leaving the station, seeing the station from the outside, and having a very clear picture of the Earth below you without being limited by a window, just looking through your visor. That is, the perfect image, and I'm really looking forward to it. I'm happy that I'm out of the water and that I actually can move my arms again, how my body is designed to move the arms, because the suit constrains a lot of my arm movement.
thought it'd be a great idea. It kind of serves its purpose, but we found better techniques like safety tether paths.
When you're in there in that position, and you've got your grabber-daddy here, and you've got your grabber-daddy and everything, just even to see the unlocked lock.
I couldn't see it. It's good to just have one wire tie dedicated to a bunny ear. So then, of course, you can pop this down and pop that up. Mine is this direction here. I like the joint to be on top because you'll find in the pool you need this to maintain your rigidity. This right now is in mortar, so in order to do the cal test, you need to either put it in retroclockwise or counterclockwise. There you go. Okay. A little different. Now you get your LED test, so now you know all your LEDs are working. Don't tether to this D-ring on the bottom. That's only for the battery. The other thing too is that you can shove this all the way in here, and then on this foot. It's not new to you. You know that you're going to go ahead and stick your boot into the toe loop, put your heel down,
and foot in, and then I lean backwards.
When we were in orbit, we had 3 spacecraft come up. We had Cygnus, we had HTV, and ATV. ATV was all the way aft, and you have to cross all of the Russian segment in order to transfer cargo to the other side. And you would really need some coordination with our Russian colleagues, because if they're working doing sport, then you're floating in the middle of their activities.
So the station does become a very busy place.
Even in shape, there are modules that are in a different position than compared to when I was up there, and the procedures have changed compared to when I was up there. Specifically the emergency procedures and all of the payloads are different. So all the training has to be done completely from zero.
The seasoned astronauts still get a kick out of looking to the future, especially when it comes to new equipment and spacecraft like the Orion capsule.
Visiting the Orion capsule today was really exciting, and it's the next stage in our space exploration. Europe is very much a firm partner in there. We're providing the service module for the first exploration missions, which is really exciting. Going back to the moon with a vision of using that same vehicle for some form of Mars transportation vehicle.
Currently, we are flying to the ISS, but the ISS program will soon, become to an end, or it will become a commercial space station. On the other hand, we are also looking to fly much deeper into space. The ISS flies at 400 kilometers altitude, and with the Orion we can actually go into deep space, for example to the moon, which is 400,000 kilometers, so 1,000 times further away than the ISS. And actually this opens a new perspective into exploration. We will go to the moon, and after the moon, we will go to Mars. And there are lots of adventures, lots of science that we can do in deep space.
Experience isn't the only thing astronauts bring back from space. Their biological specimens help evolve the gastronomical sciences.
Here we are opening the samples we received from Thomas, coming directly from the ISS. There are different samples of urine collected during 10 days of tests.
Providing enough energy for the astronauts is a critical aspect of payload planning, particularly for long-duration flights.
The centre will provide us with an inventory of all the food taken by Thomas up there for all the time of the exercises he made during the 10 days of our tests. Here, for example, we can see on this table the energy consumption of Thomas every day, how much he has spent.
You can't order pizza to go in orbit, so the decisions about what to take with them can be critical for astronauts.
Food is something that's really underestimated down here on the ground. People go like, oh yeah, I'm going to fly to space, I don't care what food I take. It's not bad. Well, you start caring about that 1 month into the mission, and then if you made the wrong decisions, it's a hard remaining 5 months. This is mainly to trigger my memory for the food that I already had, and now I can make the choices based on how I remember them. And then there's a few new ones in between. For them I have to sort of guess. There's still debate if the taste actually changes, the actual taste buds, if people perceive taste differently. My personal opinion is we don't. I think it's the same, but the cravings change, and that is really hard to predict. Right now, I might not care so much for broccoli and cauliflower, but up there, I really liked it because it's pretty protein loaded. What we have a lot of meat, and then I tried to add anything that reminds me of something green. Let's put it that way. I mean, those beans, they don't resemble beans a lot, but they actually taste really nice. Oh, we didn't have blueberries last time, right? We had raisins. That stuff is awesome. Last time I got a few Russian bonus containers. They also have very, very good food. Their food is more succulent, like they have more grease in there, also more spices, also more salt, which is not so good for the bones. So I tried not to eat so much of it. The American food or the European food is more healthy, I would say. But once in a while, it's really satisfying to just open a can of this really succulent, savory Russian food, and I absolutely enjoyed it. It's really good. On my last expedition, we tried to have the meals all together. The US crew, European crew together, we always had meals together when we could. And then on the weekends, we would gather, like the 6 of us. Either the Russians would invite us to their segment, or we would invite them. And then we have the big table, and everybody brings something together, and it's kind of this medley. That's important. Those are the relaxation moments. You can take a time, you put music on, and you chat about how your week went. And it's the last thing that I have for today, after a successful tasting of 48 items.
With experience comes cooperation. ESA is now conducting astronaut training activities in China. Samantha Cristoforetti and Ruki Matthias were each teamed with 2 taikonauts, who between them have considerable spaceflight experience.
We are basically practicing what would happen if there was an off-nominal landing. We wouldn't land on the ground, but we would actually land in the water, and we would have to survive independently for some time, and using the rescue boats and the rescue equipments, and exiting, of course, the re-entry capsule autonomously.
After donning insulation and buoyancy suits, they practiced rescue procedures with both a ship and a helicopter from a mock-up Shenzhou capsule. Space missions can be unpredictable, and training exercises such as these ensure that astronauts are prepared for every eventuality.
The training experience so far is great. The Chinese are really well prepared. It's a high-level equipment. We get helicopter airlifting. We have a huge sea survival rescue ship, which is usually employed on the high seas. So very good equipment and a very good experience so far.
Accompanying Samantha and Matthias in China were an ESA flight surgeon and a training specialist who gained insights into the different cultural nuances and approaches.
During this training, I have had the opportunity to work very closely with our Chinese medical colleagues, and I'm very, very impressed about how they have combined their traditional Chinese medicine, which has thousands of years of history, with the most advanced medical knowledge that we can find now in the world.
Training here is very, very well organized. So we have different ways of approaching training, which is inherited from the ISS program, but actually they are not that far away. So it means that we find common words and common understanding in the way they also organize this training. So for us, it's a very good sign for further cooperation with the Chinese.
This training exercise wasn't the first collaboration between the 2 space agencies. In July 2016, Chinese astronaut Ye Guangfu joined ESA's caving course in Sardinia to experience an extreme environment as part of a multicultural crew. Both activities stem from the 2015 agreement to boost collaboration between ESA and the China Manned Space Agency, with the ultimate goal of flying European astronauts on board the Chinese space station from 2022.
This joint training we are doing here is a first step in a cooperation that we all hope will lead one day in the early 2020s to a European astronaut flying with the taikonauts to the future Chinese space station. So, of course, I would be thrilled if I had that opportunity.
Organized by the Astronaut Center of China in cooperation with the Ministry of Transport's Beihai Rescue Bureau, this training session has been an important step towards long-term collaboration. Space flight opens up new horizons, not just for astronauts, but for nations as well.
Yeah, so as you know, my last mission was called the Blue Dot. We focused on the view back, the perspective back from space onto our little planet Earth as it flies through the black universe. Now, on the new mission, we decided to take a step further, to even view with a bigger perspective, to acknowledge that it's not only about our little blue planet Earth, but that there's much more out there in the universe. And as the early explorers who sailed, well, beyond the horizon, towards the horizon, and even further, we named our new mission the Horizons Mission.
The tenuous envelope of gas surrounding our planet is an unbelievably complex machine that protects us from the vacuum of space, shelters us from harmful radiation, and allows us and the biosphere to breathe. It is our atmosphere, and we need to learn much more about it so we can take better care of it. Soon the European Space Agency ESA will launch its new Earth observation satellite called Aeolus. Using cutting-edge laser technology, Aeolus will provide near real-time observations of wind profiles across the globe. These will improve the accuracy of numerical weather prediction and climate modeling, and advance our understanding of global atmospheric dynamics.
Aeolus is one of the Earth explorers that is going to look at the Earth, trying to understand the wind profiles globally. And that's the first, it doesn't exist yet. The whole idea was that we only have wind measurements on very different small spots on the Earth, and we didn't have it globally. So the mission scientists had been asking for this because it's a gap in our measurement system.
The mission aims to expand our knowledge of our atmosphere and weather systems. Aeolus will achieve this by providing global observations of wind profiles from space, providing data which has never been available before.
It's unknown ground. It's what we call uncharted territory. So we are the first agency trying to get a satellite in orbit that looks at the Earth with a laser and trying to understand the wind profile, so the direction, the height, and the wind speed. And therefore improving the weather forecast. Because nowadays we only have at single points balloons that measure the wind, or airplanes that give us some data, or at fixed points, at discrete points. This will look down to the Earth in a polar orbit, will dump every 90 minutes the data to Svalbard. That will be distributed to all the European meteorological institutes. And then when you're sitting at home on your couch, you watch the television and you see a weather forecast that is much better than we have it today.
Aeolus will fly in a sun-synchronized polar orbit 320 kilometers above Earth's surface. Its data will be sent to ESA's Svalbard ground station, located in the archipelago halfway between Norway and the North Pole, every 90 minutes. The satellite's main instrument is Aladdin.
Yes, the way the Aladdin instrument works is to eject an ultraviolet beam down through the atmosphere, and then particles of moisture in the atmosphere at various levels are in motion because of the wind, and the system measures the backscatter from those particles using the Doppler effect and can detect the wind speed at the various altitudes, and that's the way the system operates.
The development of Aeolus has been a long and difficult process, with new and cutting-edge technologies designed, developed and tested on the ground.
It has been a very difficult challenge, let's say. It's a long life, because it exists already for 16 years, the program. And when we first had the part of the instrument, when we switched it on, it worked. Then we put it in vacuum and it stopped working. And no one had realized that we needed oxygen inside the satellite to keep the laser active. So it was quite a challenge, so we had to develop a whole new set of techniques. It's maybe a bit too detailed to go in all the details, but as a lot of technology has been developed to put in this nice little satellite which is behind me.
Aeolus is another ESA Earth Explorer mission aimed at pioneering new technology while providing useful data about our ecosystem. It showcases the technological expertise of the European space industry and ESA's objective of monitoring and understanding the planet we all live on.
The main challenge for us has been within the development of the Aladdin instrument. There's a very high-powered ultraviolet laser system in there that is an inherent part of the instrument. And the technology behind that laser system, the development of a stable laser, high-powered laser beam, and the optics that then focus and divert that beam through the system is very critical, and that's been a very key part of the development. After many years and much hard work across the European industry, we've overcome those problems. We've got some new development and through coating technology on the optical surfaces to protect them. And we've now got a stable system that's been fully tested on the ground, and we're ready to go.
The tracking of air pollution is also part of the European Union's Earth observation program, Copernicus. One of the satellites that gave scientists massive amounts of data on atmospheric pollution was ENVISAT. This satellite used several spectrometers to detect ozone and trace gases in our atmosphere. The latest satellite, the Sentinel-5 precursor mission, was recently launched and builds on that legacy of ENVISAT.
So we started this precursor mission because the scientists wanted continuity of data. At the moment, we only have one spacecraft doing that job for us, which is OMI, and OMI is coming towards the end of its lifetime. The next missions that will do this job is Sentinel-4 on metopsych generation, which will only be launched in early 20s. In the meantime, to ensure a continuity of data, we need Sentinel-5 precursor. It will be the only such mission doing this job until then.
Sentinel-5B is a precursor to the Sentinel-5 mission, which should be launched around 2021. But it's not only a precursor, it's also a gap filler, because it's filling the gap based on the data that we have coming from Gomez, Kirmaki and OMI measurements towards this future Sentinel-4 and Sentinel-5 missions.
Sentinel-5P is the first atmospheric chemistry mission within Copernicus. Its main instrument is a state-of-the-art spectrometer called TROPOME, which will be used to detect trace gases in our atmosphere. The Sentinel-5P satellite is a timely replacement for the ERS and ENVISAT after it stopped working. There was an urgent need to fill the gap in observing air quality and air pollution. Furthermore, according to the World Health Organization, air pollution is responsible for over 3.7 million premature deaths worldwide every year. But the health costs are even greater, as many people suffer from non-lethal afflictions either caused or aggravated by breathing polluted air. Another major health concern on which Sentinel-5P is gathering data is the ozone in our atmosphere. When that ozone is depleted, ultraviolet light from the sun is no longer filtered. Increased exposure to UV light can cause skin cancer, immune system damage, and other ailments in humans.
The Tropomi data will be used operationally, so it will be used to improve the air quality forecasts. And air quality forecasts are of course important for people who are vulnerable to pollution, but also for the general public in case of big smog events. What we can do with the Tropomi data is we can look at the emissions of pollutants. When you see them changing over time, that is very important because we can see if certain policy measures have the right impact or where we see still increases and still have to do more to reduce the polluting emissions.
A decline in air quality such as smog poses massive risks for people's health. And one of the main contributors to climate change is the pollution of our atmosphere by greenhouse gases such as CO2 and methane. This is why measurements on air pollution need to be undertaken everywhere. Like here, for instance, with a mobile measurement station at the University of Bremen. It detects smog and industrial emissions. These local measurements supplement and validate the global observations from satellites, which in turn are needed for scientists to study the air we breathe and the planet we live on.
Well, the satellites are a key information base and knowledge base for the study of atmospheric physics, chemistry and meteorology. It's essential data because we need to know not just what's coming out at a given place, but we need to know where it's going, where it's depositing at the surface, how it's being transformed. Is it going to be taken up by clouds and rained out? If so, where? And this whole transport and transformation process is a complex business. In general, we have this problem of unambiguously identifying anthropogenic impact from natural phenomena or natural behavior in this complex system and how we're modifying it. So this is the challenge for the science, which is a necessary prerequisite to enable good legislation and ultimately sustainable development. So in this context, measurements from space are essential because they provide us with the global picture or from the local to the global scale.
The Sentinel-5P mission will have quite some improvements as compared to previous missions. For example, if you look at the spatial resolution, we will break a record, namely we will look at city scale because the nadir pixel size will be as low as 3.5 kilometers times 7 kilometers. So we can then investigate small-scale features over big cities and city agglomerates, for example.
The mission will monitor the atmosphere using the Tropomi spectrometer to monitor various trace gases in our atmosphere and reduce data gaps between ENVISAT and Sentinel-5. By combining satellite data with the local measurements on the ground, scientists can properly monitor air pollution and how it impacts us and our planet.
We have lots to understand to assess the impact. Ultimately, more pollution is bad for health, bad for people, and the estimates are somewhere between 3 and 7 million people a year die prematurely from air pollution. This is a large number of people.
At the forefront of Earth observation, the European Space Agency helps us to understand climate change and pollution by giving scientists and policymakers the data that can drive legislation.
These atmospheric measurements are extremely important for mankind. First of all, to see how our planet changes in terms of climate, but also to see how air quality changes in different places and over time. We have highly polluted areas, which are, of course, transporting pollution from one place to the other. So these fluxes of pollution or gases is very important to monitor. But also, if you take Europe, for example, Europe has introduced very strong legislation and regulations in order to reduce greenhouse gas emissions. And this has also to be verified, and these satellites are a very good measure or very good way of making sure that these reductions are taking place at a large scale.
In the early 2020s, the space component of the Copernicus atmospheric services will be extended through the addition of Sentinel-4 and 5 missions. Sentinel-4 will be a geostationary mission, whereas Sentinel-5 will be a low polar orbiting mission like Sentinel-5P. Atmospheric services are part of the Copernicus portfolio, which comprises 6 main themes: marine, land, emergency, security, climate, and atmosphere, giving a complete overview of our planet's health and its evolutions.
Can have a lot of practical applications using the data from the Sentinel-5P mission. One idea would be perhaps if we look at the harmful UV radiation, you could set up UV radiation services so that people on the street, so to speak, in the sun like today, could inform themselves how harmful it is to receive this short-wave ultraviolet radiation.
The Sentinel-5 precursor data will be combined with models and other data to develop targeted services, and they will be available as apps, social media information, or web services, so that a lot of people can choose their way they want to be informed about the environment.
Atmospheric measurements are important because especially these measurements that are done by Sentinel-5 precursor, like tropospheric ozone, information about nitrogen dioxide, sulfur dioxide, also information about aerosols, particulate matter, they have impact on the health of people. They can impact the people who have problems with their hearts or with their lungs. And as it has been shown, there are more than 400,000 premature deaths in the European Commissioning based on exposure to air pollution.
Air quality in Europe in particular, but also in the US and in Japan, got much better over the last years. That's a really big improvement. And at the same time, air quality in the developing countries, in particular in Asia, has gotten worse because they use much more energy nowadays, and that's a big source of air pollution. Also, if they are using more cars, that will pollute the air more. So it's different, depends on where you live. In some places air quality gets better, in other places air quality gets worse. I should add that in the last 3 years, air quality in China has improved because they are very ambitious about that and have very strict rules. So they are trying to follow the European or United States path in improving air quality with better technology.
Observation from space is just one of several methods of measuring atmospheric pollution. Satellites provide the data, although they need to be calibrated with measurements on the ground.
So we are offering a comprehensive analysis, integrating data at different scales. So we are using observations, we are combined with modeling, with satellite data, and all this information is complementing each other. This is the good thing of this kind of analysis. Satellite have the advantage of providing a global picture. Trends, you can study trends very well, how the main flows are taking place. But satellite data, they don't have the resolution to get in detail in the individual processes. So here, with our in situ measurements, we are getting in one particular point, and we get deeply in the detail.
the satellite gives these beautiful maps, but you can only use them really if you have a validation measurement to compare to, and this needs to be a very good measurement, and this needs to be taken on the ground. That's very important for us because we need to be very confident of the satellite data. And once you have launched the satellite, it's out of your hands and you cannot bring it to the lab and double check and test it. It's there and you need to trust the data. And the only way to get this confidence in the data is by comparison to other measurements.
Other forms of atmospheric pollution, such as the exhausting of carbon dioxide, methane and ozone, contribute greatly to climate change.
Well, I think basically it's often the case that our models, which are extremely complex and good tools, often don't necessarily have the right physics or chemistry in them to be able to predict what's going on in the future. So a lot of the time in atmospheric science we've been making discoveries. Back in the late 19th century, early 20th century, the discovery of the stratosphere was a complete surprise at the time, or fairly surprising. The fact that temperature increases above the tropopause. This was a surprising discovery, and really that's been typical. We didn't expect summer smog. We don't understand why in Paris there was a really big smog a couple of years ago in spite of improvements of legislation. This winter we had in London a smog which is maybe being attributed to excessive wood burning recently. So there's a lot of things although we're getting over the last 25 years much better information, but the satellites in particular tell us ultimately, or could tell us ultimately, what the source strengths are and enable us to follow the information and thereby, together with models, give really good prediction for people about the air quality that they're receiving.
The Copernicus program is very important for Europe and for the world. First of all, the Copernicus program is providing free data to everyone at any place in the world. So many users, not only in Europe, but also in America, in Asia, are using our data in a very large scale and very significantly. So therefore, Copernicus is really monitoring the health of our planet from all dimensions. The atmosphere, the oceans, the land surface, the ice caps, and this whole system of the Earth composed of these components is monitored constantly with Copernicus. And therefore it is really important to see what is the state of our planet and how it will evolve in the future.
Well, the data can be used for different applications. So for example, for the air quality forecasts. It's also used by KNMI, for example, for the UV forecasts. And we also use it to warn the aviation for volcanic ash plumes. On top of that, the data will also be used by scientists around the world to study the atmosphere and to study how the man is changing the atmosphere over time. Continuous monitoring is very important, especially when you're looking at slow changes, and an overlap between the data is then really necessary to be able to glue these different data sets together to one data record. And we have data records from these kind of instruments starting in the 19th, for example, for the pollution. It's very important to maintain these valuable data records and to extend them into the future.
Well, the data is important for our climate research and also for our environment, because the air we breathe, it could be changed due to all sorts of pollution events. And then a second example is that we need to monitor our ozone layer. Since ozone is destroyed due to chlorofluorocarbons, Sentinel-5P will have also the role to monitor the further evolution of the ozone layer.
Mankind can halt the pollution of our atmosphere with good legislation. The European Space Agency, ESA, works tirelessly to monitor our planet and the air we breathe.
We need a future where we, with so many people on the Earth, are in a position to maintain a good quality of living for human beings, but also for the biosphere.
New projects are advancing slowly, moving hardware into the testing phase, new designs, new capabilities. The next 12 months will see an intense rise in flight tests, demonstration launches and high-priority flights. Some are on time, others are not. Let's check the flight status of some of this new hardware and these new capabilities. Early morning at Armstrong Flight Research, Edwards, California. The Sierra Nevada Corporation's Dream Chaser sits engineless, awaiting a lift from a chopper. Lift and release. The remotely controlled lifting body makes an unpowered descent to the runway, completing another test run. The 10-year project has had its difficulties, but now the pilotless cargo ship is a step closer to a 2020 launch with cargo to the ISS. Boeing's crewed capsule, the CST-100 Starliner, has survived several high-altitude drops testing chute and airbag deployment. Weight and aerodynamic issues have pushed testing back by 8 months. Other aspects of design, however, are proceeding well, including new spacesuit designs.
We needed a suit that was airtight, could withstand the pressure differential, could get the crew down from an extremist situation, whether it was a fire or a cabin leak.
Underneath these shoulder covers is some material that we've developed that really helps provide pressurized mobility while still preserving unpressurized comfort.
You can pretty much lay there without any external cooling, right? It's that comfortable. It's something that I could stand here like this in and not have to worry about developing a big heat load.
The gas intake valves are located on the abdomen for easy access. The lightweight gloves and connections allow easier attachment and come with added technology.
A neat feature about these gloves is they have a advanced material here that enables you to interact with a capacitive touch screen. So any type of tablet you'll be able to interact with while wearing these gloves while suited fully up in the suit.
The lightweight helmet, akin to the Russian Sokol design, is attached to the suit and sealed with a zipper. The suit is designed to be worn in the capsule and not for EVA purposes, and only comes in Boeing Blue. At the same time, Boeing has the capsule trainer in service, and NASA astronauts assigned to the commercial crew roster are getting a taste for the new capsule.
what the park task trainer does is it gives you a chance to get the feel and look, where to look, how to use the procedures. When you go to a screen in the background, when I hit this button, what's it going to look like?
So I think one of the greatest things about these trainers, it gets you so used to what you're going to do. You will practice a number of times that you'll be so familiar that, like a lot of people ask, is it scary? Of course it's scary because you're sitting on a rocket, but you're very familiar with where you are.
Test schedule calls for an uncrewed orbital test later in 2018 and a manned flight at the end of 2018. This is very ambitious, however, and previous experience of spacecraft engineering suggests it may be 12 to 24 months premature. Another company with an ambitious timetable is SpaceX, whose Dragon capsule is looking for an uncrewed flight early 2018 and a manned launch 4 months later. The new breed of entrepreneurial and commercial imperatives may just make it. The interior design of this capsule is more in line with high-end sports cars. Maximum use of carbon fiber, titanium, and other lightweight alloys, coupled with the latest in electronic display and glass control surfaces. Far more commercial in feel than the usual NASA or Russian practicality and minimal comfort ergonomics.
50 meters per second. Slightly below nominal. We're over 1 kilometer. Truck deploy. Trucks look good. Sequencing the mains.
Their capsule is well along its testing phase, having completed both static and pad abort exercises, including parachute deployment test. A wild ride indeed. With room for a crew of 7, the Dragon capsule may well be the first commercial entity to launch and land astronauts from the ISS within a year. Unity spaceplane of Virgin Galactic has been building its test credentials slowly but steadily. Having suffered catastrophic failures in the past, they are fully focused on safety. Ground crew operations of both the spacecraft and its carrier plane are rehearsed ad infinitum, training and checking as flawless procedures evolve. Motor testing again and again. Unpowered flights, carried aloft by the White Knight 2. Rehearsing with ever greater complexity, the latest flights fully loaded with rocket motor and propellant tanks. The pilots performing a perfect landing. Next step, a powered suborbital flight, perhaps sometime in the next 12 months. The The newest space-capable nation, New Zealand, is preparing the second launch of its Electron rocket. Powered by Rocket Lab's homegrown 3D-printed Rutherford engine, their second test launch is imminent, designed for the small satellites in low Earth orbit at a fraction of the standard cost. If this second test launch is successful, then Rocket Lab may drop the third and final test flight in favor of full commercial deployment next year. Blue Origin's reusable new Shepard rocket and capsule system has proceeded successfully through the testing phase, including launch abort and single parachute landings. It won't be long before 6 paying passengers will fly into space.
New Shepard has cleared the tower.
There it is, 70,000 pounds of thrust pushing that crew capsule.
Okay, so those 3 mains are reefed right now to keep them small. The reefing will remove shortly to fully expand, as you can see.
And touchdown of the New Shepard crew capsule.
Blue Origin is also developing a multi-stage version to reach orbit. The new Glenn could send payloads or passengers into orbit with a 2- or 3-stage variant, although it is still some years away. Delayed several times from an over-enthusiastic launch timeline, the Falcon Heavy will undergo a static fire test of all its 27 engines in the coming weeks. The first test flight will follow within the first 2 or 3 months of the new year. NASA's Space Launch System has hit further snags in development, namely issues with the welds of the enormous fuel tanks. Not unexpected, as the new technologies and manufacturing techniques evolve. Delays in delivering the Orion's EMS propulsion system have also set back the timetable, with 2020 likely to be the earliest a flight could take place. The James Webb Telescope has also been delayed by a year. A planned Ariane 5 launch will hopefully take place mid-2019. Ariane 5, Soyuz and Vega launches are due for an upgrade. At the European spaceport in Kourou, French Guiana, the new launch facilities for ESA's Ariane 6 launcher are being built. At least the big hole is there, the excavation is done, and the launch zone buildings will soon appear on schedule.
The independent access to space is, of course, the primary objective. And we always used European developed launchers to fulfill this objective. We were lucky enough that we were very successful also on the commercial market with Ariane 5. We still have over 50% of the commercial market. As we all know, this environment is exposed to fierce competition. The offer of launch vehicles from 2020 onwards will be significantly higher, and we have designed Ariane 6. We have designed it to cost. We have designed it to be able to go against this fierce competition in 2020 onwards. And for this, of course, we also use this launcher to deploy European flagship programs like Galileo.
This move is associated with a change in the governance of the European launcher sector, based on a sharing of responsibility, cost and risk by ESA and private industry.
We are in the middle of the full development of the launcher Ariane 6 and of the base, which is ELA-4 in Kourou. I can say that currently everything goes well. It's on track. We are now in the situation where the configuration is clear. We know exactly what the configurations are with the Ariane 62 and the Ariane 64. The first one is for institutional payloads, mainly because it's a single payload version, where we can launch up to 4.5 tons in a sun-synchronous orbit. And the Ariane 64 enables a dual launch, which goes up to 10.5 tons in an equivalent geostationary transfer orbit.
ESA and its member states have a new role in Ariane 6 in the sense that we change governance. Governance by giving more responsibility to industry, to the private sector, while the public sector has defined the high-level requirements, which means that we said we want a cheaper launcher, we said we want an environmental friendly launcher, we want a flexible launcher, and this is absolutely key in the current situation to be ready to catch new markets, and Ariane 6 will be the right response to that. We can say that European industries are working full speed ahead. We just had Maturity Gate 6, what we call, where we can consolidate the industrial structure. We aim at starting the first batch of production next year, spring next year. So now we can say the industries are ready, they are full speed ahead, and we will start to produce Ariane 6 from next year onwards. It is very clear, in a definition of a space power, the independent access to space is part of it. Ariane 6 and Vega C is the new family of the European independent access to space.
Vega C will cover the deployment of the Sentinel satellites for the EU's Copernicus program. Vega C will increase Vega's current capacity from 1.5 to 2.2 tons on polar orbit, which is the most common for observation satellites. For Ariane 6, the pad will be different from previous launches in Kourou, with a horizontal preparation of the stages. The first launch is still on target for sometime in 2020. Although there are extensive works going on at Kourou, they will not affect the upcoming Vega launch of the European Aeolus satellite, slated for early 2018. next major launch is the TESS exoplanet survey mission. The satellite has completed pre-flight tests and is the first NASA astrophysics satellite to be launched under contract with SpaceX. The current launch window of the Falcon 9 is no earlier than March 2018 and not later than June 2018. The second exoplanet hunter, Cheops, is on schedule as well.
The satellite is commissioned by ESA. The project is being led by the University of Bern. They also built the instrument. That's the main part of the satellite. And the satellite structure, the platform with all the housekeeping, is built by Airbus in Madrid.
The satellite has gone through rigorous pre-flight tests, including vibration, acoustic and vacuum chamber tortures, and is on track for a late 2018 launch aboard a Soyuz launcher.
Gaz hume avec AM. Allumage triétage. À tous de DDO. Attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Top. Et décollage VS12.
Bepi Colombo, the joint JAXA-ESA project bound for Mercury, is ready to launch. The mission consists of multiple parts, including the Mercury Transfer Module, a sun shield, and two scientific orbiters, ESA's Mercury Planetary Orbiter and JAXA's Mercury Magnetospheric Orbiter. The spacecraft was assembled in its launch configuration inside a clean room at the European Space Research and Technology Centre, or ESTEC, in Nordwijk, in the Netherlands. It has been dispatched to the spaceport in Kourou for its mid-2018 launch and 7-year flight to Mercury. For over 50 years, we have bombarded Mars with our probes and landers, spying from orbit to map the terrain, finding her strengths and weaknesses. On the surface, probing for her resources and learning of her defenses. The next generation of robots are readying to establish the beachhead. The time is approaching for the full-scale invasion of the planet, when humans walk on Mars and claim it for their own. The conquest of this enigmatic planet so far away has been both challenging and rewarding. ESA has delivered the latest conspirator, the ExoMars Trace Gas Orbiter, to search out the source of methane in the atmosphere. Its landing craft, the Schiaparelli lander, failed and crashed, yet another victim of Mars's defenses. The ExoMars orbiter, now captured by Mars's gravity, has begun the challenging process of adjusting to a circular orbit without fuel. This involved using the shifting Martian atmosphere to gradually slow the satellite in a process known as aerobraking.
With ExoMars, ESA is going to use for the first time a method called aerobraking for a spacecraft in orbit around Mars to decrease the orbit by letting it fly through the atmosphere and using the atmospheric density to slow it down instead of using fuel for the engines.
We have to take a lot of margin to be sure that even if we go through a moment where the atmosphere is more dense at the altitude where we are flying, we are still safe with the spacecraft.
That aerobraking process took more than a year to complete. It was complicated by the changing nature of the Martian atmosphere.
The Trace Gas Orbiter is really looking at active processes ongoing on Mars today, and life, present life, is one of the possible explanations. So it will be really a Sherlock Holmes work to try to put together a case for whether it's geological or biological activity that is responsible for the methane.
Meanwhile, plans are well advanced for the ExoMars 2020 mission, with the final design of the rover nearing completion. And scientists have shortlisted two possible landing sites to put it to use: Oxia Planum and Morth Vallis. Both are shortlisted because they have had an abundance of water in the planet's early history, the main building block for life.
First of all, we want a landing site that is ancient, because the hypothesis is that conditions on the surface of Mars 4.3 to 3.9 billion years ago were similar to those on Earth when life started here. So the site has to be old. The second condition is we want a site where we had liquid water present over hundreds of millions of years. And we want this liquid water to be what we call low energy or slow flowing water, like on the canals in Amsterdam.
The rover then scouts around for the ideal locations and, with its driller apparatus, digs deep into the Earth to extract soil samples which will be placed into its onboard chemical analysis equipment, hoping to find ancient signs of life. Beginning this year, the next wave of spacecraft begin their sojourn to the Red Planet. NASA's InSight mission, the first to be launched from Vandenberg Air Force Base in California for another planet, is preparing for liftoff. The vehicle had already been through its pre-flight test and had been shipped to the launch facility. It is crucial that all aspects of the lander are in perfect operational readiness. The probe is destined for the equatorial region of Mars and will look deep into the heart of the planet.
The InSight mission is a geophysical mission to Mars. It's going to go to Mars and take its vital signs. It's going to take its heartbeat, the seismic activity of the planet.
So we're going to be doing that using a seismometer, a very high precision seismometer, using techniques that have been well developed on Earth to get the understanding of the crust, mantle, and core, and sort of the relationship between those.
Going to take its temperature by measuring the thermal gradient of the surface, which tells how much heat is coming out.
We also have a heat flow probe, we call it HP cubed, and what that does is it's going to basically take the temperature of Mars, and from that it'll be able to understand what the thermal flux is over the course of a full Martian year.
And it's going to sort of measure its reflexes by looking at how the rotation wobbles with the tidal effects of the sun.
Our final experiment is called RISE, and that's going to be looking at basically the wobble of Mars to help understand what the core size may be and composition.
InSight isn't just a Mars mission, it's really a mission to the terrestrial planet interiors. So Mars is kind of the Goldilocks planets. It's not too big, it's not too small, it's just right. If it was too big, it would have retained a lot of activity and erased all the evidence that we're looking for. If it was too small, it never would have undergone the same processes that formed the Earth, and so it's really just right.
Mars will give us this insight into early planet formation and early planetary processes.
Understanding the details of the structure of the interior of Mars will allow us to address questions of planetary formation that we've only been able to guess at before.
We are missing cold, hard data, and this is what this mission will provide.
Meanwhile, NASA, ESA, and the Russians are continuing their programs. Soon, new missions from China, Japan, India, and the United Arab Emirates will begin. Getting humans to Mars is the pressing goal of NASA and other adventurous parties. Many big aerospace corporations contractors have all been at the drawing board working out the immense engineering and logistical challenges. They all concur that to get to Mars, you need more than a big rocket. NASA's SLS and Orion spacecraft are only two of many components that will be needed. With some more political emphasis, NASA, in concert with other agencies including ESA, Canada and the Russian space agencies, are able to push ahead with the Gateway Facility concept. Effectively building a space station in cislunar orbit between the Moon and Earth, it would be a staging post for a return to the Moon, the gathering of resources from the lunar surface, and an assembly point for a Mars flight and beyond. Orbital ATK is one of 6 companies selected for NASA's Next Step 2 program, a public-private partnership for commercial development of deep space exploration. Not the first to suggest the Moon be a staging post, Orbital ATK recommends a parking orbit in cislunar space built from its successful Cygnus cargo craft. First, they will launch an initial habitat module aboard NASA's heavy-lift SLS rocket with a crewed Orion capsule. Placed in a parking orbit, it will act as a platform for experiments and serve as a destination for future crewed missions. By 2025, additional modules would be added to the habitat, allowing deliveries of crew supplies and experiments, and serve as a waste disposal vehicle at the end of their missions. The modularity of the system also allows for multiple visiting vehicles, providing a base for lunar sorties. Mining for resources, in particular water, would allow for more cost-effective and longer duration missions to Mars. From water you gain hydrogen for fuel, oxygen as the oxidizer, and for breathing, and of course, drinking water.
We have places on Moon which are, at least especially at the South Pole, which has permanent darkness, where we can find water, and we know from some missions that there is water. Water is a good source to produce hydrogen and oxygen. And also to go into the shadow of the Moon, we will have places where we don't have the radiation coming from the Earth. So building a telescope over there by using the material we find on the Moon, so not bringing all the stuff from the Earth, that could also open new possibilities to look deep into our universe.
These crewed missions would also help with man's understanding of how we can best survive long-duration space exploration. By 2030, with additional modules, the habitat could be expanded to provide a Mars transit capability for demonstration expeditions lasting 1,000 days or more. Boeing, the primary contractor for the SLS rocket system, believe their plan will require 5 or 6 SLS launches to be able to get to Mars.
So we want to make sure that we've checked everything out and that we know that it's good to go before we actually leave for Mars. Because once we leave, we can't come back for over 2 years. And the reason for this is because it's the alignment of the planets. The way the planets revolve around the sun, it allows a window of opportunity to go from Earth to Mars basically every 2 years. Just to get to Mars, before you even land or anything, is going to take 7 or 8 months. The reality is you're going to be there for a year waiting until that window opens up to come back. And then it's going to take 7 or 8 months to come home.
Having a cislunar outpost enables international partnerships and commercial opportunities, such as exploration of the lunar surface and scientific and technological research. After cislunar space, we'll start the actual missions to Mars. The first mission will be to Mars orbit. This mission will teach us about the space systems that will take us to Mars and back. The next mission will send humans to the surface of Mars. The crews will undertake detailed scientific research and investigation. They will start to unlock the secrets of Mars.
Their initial concept, now under development, consists of a power and propulsion bus to provide electric power and propulsion, 2 habitat modules, an airlock module, and a logistic work module, then supplied by cargo and crewed modules from the US and Russia. And finally, it could be used as the vehicle and habitat for long-term exploration of space. Lockheed Martin's concept for transporting to Mars has resulted in a holistic view of the mission. They too will assemble the space gateway in cislunar orbit. This will provide the platform to build the Mars Space Base Camp and get it ready for flights to Mars. They see that Orion is a part of a larger system that provides the supplies and the scientific equipment needed for the journey. This resulted in what they are calling Mars Base Camp. Mars Base Camp is an orbiting mission with 4 main sections and 2 of almost everything for backup. Four large commercial solar arrays to generate electricity to power the spacecraft. For propulsion, we have 2 cryogenic stages, one either end, and 2 tank farms to store the fuel and oxidizer. Within those stacks lie 2 habitat modules and a large central living space to eat, sleep, and exercise. Most importantly, we have Orion. It is the command deck with all the avionics, navigation, and communications. Orion makes the spacecraft more reliable and gives the astronauts a safe ride home. The orbiting crew could also investigate the 2 moons of Mars, Phobos and Deimos, deploying landers or robots for sampling, even astronauts to explore the surfaces of these moons. The main mission, however, will, after careful examination, confirm a landing site for the next mission and the first human landing. From orbit, the astronaut scientists will have access to the entire planet's surface for rovers and drones to be able to make real-time decisions about where to go and what to examine, retrieving samples from the surface for study. Lockheed Martin's concept, the almost retro rocket ship, the MEDV Lander, is their design for a reusable launch and landing vehicle and is based on the current technology, including the Orion and shuttle systems, and not as far-fetched as first thought. Reusability and innovation will conquer Mars. Keeping costs down will make it viable, and making it doable is innovation. That's something that SpaceX is founded on. Their BFR is the direct Mars transport system, from liftoff on a reusable booster, a short time parked in low Earth orbit for a fuel top-up, then direct to Mars and a 3-month cruise, then landing directly on the surface of the red planet, ready to be refueled from local resources for the return journey, landing back on Earth in the one reusable spacecraft. In the meantime, SpaceX is testing its Falcon heavy rocket system in preparation for its maiden voyage. One of the issues of flights to Mars, which is addressed in part by the BFR, is the cruise time. In theory, SpaceX has it down to 3 months. The other NASA-led systems will take 7 to 8 months, a long time to house, feed and power a crew with little to do. Getting there much faster would be a game changer. One possible way to achieve this is nuclear power. Nuclear thermal propulsion, or NTP, could enable faster transit time both to Mars and beyond. NTP is powered by nuclear fission. How it works is conceptually simple. Energy from fission is used to heat a hydrogen propellant to about 2,420 degrees Celsius. This hydrogen is then accelerated through an exhaust nozzle, resulting in a propellant efficiency roughly twice that of the best chemical rocket engines. For example, it may be possible to fuel modern NTP systems with low-enriched uranium instead of highly enriched. The physical size of an NTP engine is largely determined by the rate at which fission energy can be transferred to the hydrogen propellant, but the equivalent volume of the uranium that would be split is actually quite small, roughly that of a toy marble. Getting travelers to Mars faster, NTP can take months off the trip compared to using traditional chemical systems. This would reduce the need for payload, food, and power for the crew, minimizing the risks associated with exposure to galactic cosmic radiation, microgravity, and other hazards of deep space travel. The maturation of nuclear thermal propulsion will also promote the successful development of the kilopower fission power systems for use on the Moon, Mars, and other destinations, as a main source in situ for life support, communication, industrial and other diverse applications. Harnessing first-generation NTP systems is a first step towards advanced nuclear propulsion systems capable of travel throughout the solar system. The amazing Cassini spacecraft and its sibling lander Huygens have now concluded their scientific studies, bringing back years of data to be combed through by scientists, plotting their next journey to Saturn's space. Now it's time for other planets and other spacecraft to shine. Juno piercing the cloak of Jupiter, and her distant relative New Horizons at the edge of the solar system. After 20 years, the Cassini project finally comes to an end in dramatic style. But with one door closing, another opens. Now the enviable task of having to unravel the data Saturn has just laid bare begins. And they have literally just scratched the surface.
I think Cassini has left us with humankind's presence at another planet for 13 years, seeing things that we had never imagined seeing, and at the same time sharing that with the entire world and opening up vistas for the next sets of missions.
One of the issues facing scientists when looking at exploring the new frontier is leaving it in a better state than they found it. So eliminating the problems of space junk or the introduction of alien microbes is paramount in their decision-making.
But it also helps us satisfy a planetary protection requirement. We're protecting the tiny moon Enceladus as well as Titan. Both of those have global oceans underneath their icy crusts, and just in case there might be life in those oceans, we don't want Cassini to crash into one of those moons once we're out of fuel.
While the main focus of the Cassini mission was to delve into the mysteries of Saturn and its rings, the moons of Saturn proved most science-worthy. And Saturn has many moons. In fact, 62 with confirmed orbits. Several are only 50 kilometers in diameter, the largest being Titan, which is bigger than Mercury. The Huygens module that travelled aboard Cassini also became the first probe to land on a moon other than our own and transmit data back to Earth.
The temperature at the surface of Titan is about minus 180 degrees, so it's very cold. The landscapes of Titan look a lot like those we have on Earth. We have rivers, lakes, seas, almost oceans of methane. It rains methane or a mix of ethane and methane, so there are lots of meteorological phenomena or geophysical phenomena on Titan that makes you think of what happens on Earth. But the ingredients are quite different.
But it is Saturn's sixth largest moon that excited many scientists, as it is virtually covered by clean ice and ejected plumes of water into space.
My favorite moon is Enceladus, and the reason I'm partial to Enceladus is it's the moon that my team discovered a water vapor plume at. But not only is there liquid water underneath the surface, but there's organic material, there's a heat source. And you know, when people get excited about the potential for life elsewhere in the solar system, there are four things that you need. You need a heat source, you need liquid water, you need organic material, and you need those three things to be stable over some period of time so that life could potentially form. At Enceladus, we've got three. We're not sure about the stability over time yet. And so based on the Cassini observations we made back in 2005, we've had lots and lots more flybys of Enceladus. We now understand it much better. We understand what organic material is there. I mean, one of the instruments, the ion neutral mass spectrometer, in a very close flyby through the plume, found some ammonia in the plume.
First of all, we see plumes. Then we start finding out from the gravity measurements and the imaging that there's an ocean and that it's global. And then there was some measurements by the cosmic dust analyzer that suggested there was hot water being circulated through the rock, the silicon dioxide nanoparticles. This is just the final step that shows that there's molecular hydrogen being produced by these same hydrothermal processes, and that molecular hydrogen has the chemical energy to support microbial systems in the interior ocean.
It's really the longevity of the Cassini mission that's allowed us to put together the pieces of the puzzle to really understand a moon like Enceladus. And even this late in the mission, we continue to look at our data to better understand this ocean world.
Collating data is one thing, but interpreting and providing vision for future missions is another. This is an area for which the Cassini project came up trumped, because it not only brought together three agencies, it provided the ground for future scientists to develop skills that will provide the basis for new projects.
The number of PhDs we've put through the system that are going to be the educators of the next generations. We've put out 3,000 plus peer-reviewed papers, hundreds of PhDs, thousands of peer-reviewed papers. The legacy, the scientific legacy is huge. The engineering legacy, of using every ounce of engineering capability to exploit a system, I think is again, we will be built upon. And I can't ignore the international cooperation. I mean, we had 19 nations contributing hardware to this mission. We've got over 26 nations now contributing scientifically.
The mighty Jupiter is the current target under the microscope with the Juno mission in full swing. The story of our solar system is linked to Jupiter, as it is believed that it was the first planet formed. So if we can understand how, we can begin to unravel the origins of our solar system, and thus how the Earth came about. Juno must work in a very harsh environment to tease out the answers from the gas giant.
When you go to a place as hazardous as Jupiter, we put a lot of time through the whole development process in trying to design a spacecraft that will operate in the high radiation fields, the magnetic environment, the spacecraft charging environment, everything that you do with the Jupiter. And I have to say the spacecraft has been performing admirably.
Jupiter's radiation belts pose one of the biggest problems faced by Juno scientists. They exist within the enormous magnetic field that surrounds Jupiter, with its magnetosphere trapping and accelerating particles. It produces intense belts of radiation, similar to Earth's Van Allen belts, but thousands of times stronger.
Juno just flew by Jupiter for the first time with all the science instruments on, and it was spectacular. The spacecraft performed flawlessly, the instruments all worked exactly as planned, and the data is amazing. We're looking deep into Jupiter, we're learning about the secrets that it's holding, but we're also getting a lot of surprises about the aurora, about the atmosphere, how it works. I mean, it's just incredible.
The flybys which followed showed that the massive amounts of energy swirling over Jupiter's polar regions were creating the giant planet's powerful auroras, but not in ways the researchers expected. What puzzled the researchers was the fact that despite the magnitude of these potentials at Jupiter, they are observed only sometimes, and are not the source of the most intense auroras as they are on Earth.
Juno had its camera, JunoCam, on during the flyby. We got the first pictures of Jupiter's poles, the North and South Pole. They were amazing, a lot of surprises, and it didn't look like we thought. Doesn't look much like Saturn's pole.
Jupiter's poles are covered in these cyclones and anticyclone storms, some of them half the size of the Earth or bigger. And we're puzzled as to how they could be formed and stable in that configuration. And the North Pole doesn't look like the South Pole. And so we're questioning, the scientists are really questioning whether this is a dynamic system and are we seeing just one stage and over the next year we're going to watch it disappear? Or is this a stable configuration and that these storms are circulating around each other?
While the polar activity appears unique to our solar system, the engineers are looking below its shell for answers.
The new science results from Juno really are our first look at close up at how Jupiter works. And so the first time we're looking inside of Jupiter with into the interior, and what we're seeing is that it doesn't work at all like we had predicted. Almost every model that has the interior motion, how the magnetic field, the gravity field, how the deep atmosphere works, it's all different.
Like most scientific undertakings, they result in more questions being asked than answered.
So Juno's original objectives really were to understand how Jupiter formed, and that would help us understand how planets general form and how the whole solar system was made. What we're finding is that actually we didn't understand giant planet dynamics very well, the whole atmosphere or interior structure.
What we've seen so far is exciting, no question about that. But it's like a puzzle, and we're putting the pieces of the puzzle together, and it's exciting, but we don't have the whole picture yet.
And one of those puzzles is the so-called Great Red Spot. And while its presence in a turbulent gases planet is not unusual, the scale is. The red spot covers an area twice as large as Earth.
And we're going to go right over the Great Red Spot. And that's really going to be the first time that we get a close look at that and to see what it's like underneath the top surface layer. I mean, how deep are the roots to that? That's a 300-year-old storm. A lot of scientists believe that the roots must be very deep. Well, when we go over with our microwave radiometer, we're going to see, is it the same as the zones and belts, or is it very different? And nobody really knows.
But it's not just Jupiter's poles that hold the greatest interest for the Juno investigators. They are also intrigued by the weather pattern that is unique to this planet, yet familiar in other ways. Studying the atmospheric dynamics helps understand other planets' atmospheres.
So when we look at Jupiter, we see a lot of structure that looks very similar to the Earth. We can see storms, we see cyclones, we see anticyclones, and these sort of storms and weather systems that we see on Earth are very similar, and they're happening on Jupiter. Fluid mechanics is hopefully the same everywhere in the universe, but Jupiter and Earth are very different. Jupiter is much bigger, it rotates a lot faster, they're made of different material, and Jupiter's much further away from the sun than the Earth is. The quasi-biennial oscillation, or the QBO, on Earth is an equatorial phenomenon in the stratosphere where the winds are changing direction approximately every 2 years. Depending on which phase the QBO is in, eastward or westward, the temperature signal corresponds to that. So it's warmer in the eastward phase and cooler in the westward phase. It's been shown that it can actually be a barrier to transport of aerosols across the equator and has been linked to the frequency and the formation of hurricanes in the Atlantic and the Pacific Ocean. The long-term scales on Earth's climate is something that we're very interested in, and how that applies to other planets' atmospheres is really why we're studying Earth and Jupiter. The quasi-quadrennial oscillation in Jupiter's stratosphere is a temperature signal that we see in the equator, where we see the temperature get warmer and cooler approximately every 4 Earth years. We used a general circulation model where we focused on simulating the effects of small-scale waves produced from convection in Jupiter's equatorial region to simulate the QQO. The waves propagate upwards from the clouds and force the winds in the stratosphere to change direction, going from eastward to westward approximately every 4 years. Our model was able to reproduce the behavior of the QQO, but was also able to reproduce temperatures from the observations, and both of those together give us a lot of confidence that our model is very accurate in what's driving the QQO. The outer planets serve as a laboratory for understanding atmospheric physics under very different conditions that are present on the Earth. Understanding how their atmospheres change and evolve and their climates can give us insight into any planetary atmosphere.
Juno has studied the planet with a suite of tools revealing much that was previously hidden to the human eye.
We have an infrared instrument on Juno called JURAM, and it was designed and built and delivered by the Italian Space Agency. And this instrument makes thermal maps of Jupiter. So the images are showing you what's warm, hot, cold on Jupiter. And one of the things you can see right away is the center of some of these hurricane-like storms are cooler than the surrounding area. And sometimes you go over a warm spot. And we went over one that was very small that seems hotter than the surrounding area. And that's very similar to what the Galileo probe went into back in 1995.
The Juno mission is unique because it's the first time that we've ever gone in a polar orbit, which goes from pole to pole, over the North Pole, through periapsis, and under the South Pole. All the other missions we've done and all the observations we made from Earth were made from the equator. And you don't see the poles very well if you're sitting on the equator. Yes, this is the first time we get the first clear, unobstructed view of what the aurora looks like and what the polar phenomena looks like. And at the same time, we're flying through the magnetosphere right above the aurora, so we can sample in situ the charged particles that are precipitating down magnetic field lines, the guys that are exciting the emissions that we see.
Juno, like its sister Cassini, has a use-by date when the craft runs out of maneuvering fuel. This may occur during its 12th orbit at the end of its prime mission. However, NASA may choose to extend the mission if there are sufficient reserves. In that case, the deorbit would occur later, on the 34th orbit, as part of the planetary protection policy of NASA. Its pathfinding mission is leading the way for the one to come, the Europa Clipper, a mission in the design phase to look closely at Europa, the moon with a hidden ocean, and the possible location for life to evolve beyond Earth. The blue haze of Pluto's atmosphere, possibly a hydrocarbon smog, seen from 200,000 kilometers away by NASA's departing New Horizons spacecraft. A few years ago, the dwarf planet Pluto and its 5 known moons were just small dots in the outer reaches of our solar system.
One of the important things you should understand about Pluto is the real scale of it compared to the rest of the solar system. So we've come to the beach to really convey that scale and distance. So if I draw the sun as a 30-centimeter circle, then we have to walk about 35 steps this way in order to draw the Earth in the same type of scale. So we're walking the equivalent of 150 million kilometers, which we call 1 astronomical unit. Normally, Pluto orbits at about 40 astronomical units from the Sun, but it's actually quite an elliptical orbit, so it changes between about 30 and 50 astronomical units. But back to the Earth. So the Sun is over there at 30 centimeters, which means that the Earth should be about here, about 3 millimeters, something like this. If we were to draw Pluto in the same scale, it should be 0.3 millimeters, and it should be 1 kilometer down the beach. So I'm going to draw it. Now obviously I can't draw something that's 0.3 millimeters, so I have to draw Pluto a bit bigger. If this is Pluto, then its largest moon is Charon, which is about half its size. But Pluto has 4 other moons: Styx, Nix, Kerberos and Hydra. So there's a lot going on around the Pluto system. It's not just a cold, dead, icy rock.
The spacecraft spent 16 months sending its data back to Earth, and scientists and non-scientists alike have been enthralled by what it has revealed.
If you go in closer to the surface, you can see this type of really diverse terrain. So you have a very bright region. These are flat plains. Not entirely sure how they formed yet, but there's a couple of leading theories. There's a huge range of mountains. There's all kinds of different aged surfaces. Some of them have lots of craters. Some of them have very few, which means they're younger. If you look at in a lot of detail at some of the mountainous regions, you can see that actually they're a few kilometers high, but they're made of water ice. I mean, on Pluto, it's so cold that water ice is the hardest thing. It's more like rock. And so the stuff that forms the softer material is actually nitrogen ice.
Water ice on Earth is close to 0 degrees, but on Pluto, it's minus 230 degrees Celsius. And there's a glacier of nitrogen ice, called Sputnik Planitia, thought to be under 1 million years old. This is young by planetary standards, and no one knows yet how it formed or is renewed.
One of the really fascinating things is some of the surface coloration you can see in these images actually shows that there are these compounds called tholins, which are a combination of elements, but they're related to prebiotic molecules, so they're kind of relevant to prebiotic chemistry. And I think the fact that they have been able to form on planetary surfaces very far out in the solar system at very cold temperatures really has implications for a lot of places. I mean, if you can imagine for star systems outside our own, where the star may be dim and the planets are quite far away, it's interesting to know that there are molecules that could be involved in supplying biotic material to processes that may one day lead to life or be involved in life or something like that. They're actually forming way out in the solar system where no one really expected.
Pluto is unlike anything seen before. But the 6 gigabytes of New Horizons images and scientific measurements are giving scientists mysteries to unravel for years to come. In the meantime, asleep for the moment, the probe travels deeper into the unknown, soon to awaken at its next destination.